Very good evening, friends. See, today we are just starting with this the intense revision program. We have planned the entire geography. I thought of completing in 6 days or 6 classes of 2 hours each, where I'll try to cover, say, for example, almost all important areas of geography. Right? When I say important areas of geography, mostly, right, this analysis is based on the previous year's questions as such. So where exactly the larger number of questions have been asked, or at least the certainty of the question is asked. So there, those areas will be covering in general. And of course, since this is say for example, almost it's more of a revision, right? Intensified revision, right? Somewhere in-depth analysis we may not be doing it because that is not practical. So the very important gist of this subject we'll be taking and we'll be discussing. Okay, right, right, my dear friends. So today we'll just start with geography. The likely topic what exactly we'll be trying to cover today. We'll be trying to cover this entire geomorphology, world physical geography. I'll, I'll try to cover this geomorphology, my dear friends. And the likely topic that what we'll be covering today, some of those topics, we'll be talking about the internal structure of the Earth, the continental drift theory, plate tectonic theory, volcanic activity, earthquake, tsunami, and of course the types of rock, right? Only the basic, the gist, what is very, very important, only those things we'll be discussing. Okay, right. Right, my friends. Having said this, one by one, I'll just start talking about. And if at all, if some of the topics were there in news, we'll be giving more emphasis to the same. Right. In that way, we'll just start with the internal structure of the Earth. And let me also tell you, when I talk about this internal structure of the Earth, it was there in news. Right. Very recently, you would have come across a fact saying that, right, the inner core of the Earth, somewhere it is believed that it stopped rotating. Normally, we have an idea that inner core, right? Core itself is divided into two layers, the inner solid core and the outer liquid core. So this inner solid core actually goes for a rotation, right? Like a swing, it will be, say, for example, rotating in both the direction. For example, the complete cycle approximately, it is for 70 years. So in one direction, approximately it rotates for 35 years, and another 35 years, it will be rotating what? The opposite direction. This is what the normal average, say for example, this, the rotational type is all about. Okay. So very recently, they have concluded that way back in 2009, it came to a halt. Okay. It is just a belief. And it was a study that was, say for example, somewhere, the finding of the study was somewhere it was published. Okay. So having taken the clue from that, somewhere I believe that internal structure of the Earth is very important for this year. Accordingly, my dear friends, we discuss about this internal structure of the Earth. Right. In that way, Earth's interior has plenty of layers. Plenty of layers. Right. Say for example, the outermost layer we call them as what? The crust. The middle layer we call them as mantle. The innermost layer we call them as what? Core. This is one way of classification. There is one more way of classification. The outermost layer, you call them as what? Lithosphere. Below lithosphere, you have a layer called as asthenosphere. Below asthenosphere, we have mesosphere. Below that, we have outer liquid core and inner solid core. So, when I talk about the classification of this Earth's interior, we can classify them into two bases, or say, for example, on two different bases, we can classify them. One, we can classify them based on the composition, what exactly these layers are majorly composed of, what is the building element, or what exactly is the building material, right? This is one way of classification, right? There is one more way of classification, my dear friends. What is this one more way of classification, if you ask me? It is based on the mechanical state of matter. It is based on the mechanical state of matter. When I say it is based on the mechanical state of matter, my dear friends, whether it is solid or liquid, right? Or say for example any other state of matter, somewhere we have to, right, classify based on that. In that order, the outermost solid layer we call them as lithosphere. Below lithosphere we have a partially molten layer called as asthenosphere, and any middle layer we call them as what? Mesosphere. And say for example that part of core, right, the outer layer of this core we call them as what? The outer liquid core. And say for example the inner core we call them as what? Inner solid core. Okay, so somewhere this Earth's interior can be classified either based on the composition or it can be classified based on the mechanical state of the matter, right? So you have composition layer as well as mechanical layer. What is very popular is this compositional layer. See, there is a greater degree of overlapping, but I understand one is not the same as another. For example, sometimes we say the outermost layer of the Earth, we call them as crust. Sometimes we say the outermost layer of the Earth is called as lithosphere. But what I understand, entire crust is lithosphere, but entire lithosphere is not crust. Because the lower lithosphere I have, the lower lithosphere is more like what? Mantle. Okay? It is more like a mantle. Find my difference now. Right. Just give me a minute. Right. The composition layer and the mechanical layer, right? We have just taken it. What is very important, as I said, composition layer is very, very important. We'll just somewhere discuss about the basic facts about the composition layer as such. Okay. In that order, my dear friends, the very first layer, the outermost layer, we call them as what? Crust, right? We call them as crust. And let me also tell you, say for example, whenever the demarcation of this composition layer, we mark it by a discontinuity. We mark it by a discontinuity, right? So what separates crust and mantle, if you ask me, we have a discontinuity called as Mohs discontinuity, or you call them as what? Mohrovich discontinuity. Okay. And similarly, when I talk about mantle and core is separated by another discontinuity called as Gutenberg's discontinuity. So both the discontinuities are very important because they are major discontinuities. Among them, we do have minor discontinuities, my dear friends. Okay. In between, say for example, within the crust, we have a discontinuity called as Conard. Within the mantle, we have a discontinuity called as Rapiti. And within the core, we have a discontinuity called as Lehmann's discontinuity. So somewhere, my intuition says that this Lehmann's discontinuity this year may be slightly important because what separates the outer liquid core and inner solid core is this discontinuity called as Lehmann's discontinuity. So the name discontinuity was given for the simple fact that these are the layers where the earthquake waves or seismic waves will get refracted largely, right? A small or a very small discontinuity you will experience with respect to what? Seismic waves. That's the reason you call them as what? Discontinuity. So somewhere my intuition says that Lehmann's discontinuity this year may be slightly important, right? Because core was there in news. Okay. Alongside Gutenberg's discontinuity also kindly try to remember, right? So when I talk about, say, for example, Gutenberg's discontinuity, it's a major discontinuity, right? What separates mantle and core is Gutenberg's discontinuity. And what separates this outer liquid core and inner solid core, as I said, it is Lehmann's discontinuity, right? Lehmann's discontinuity. Both are equally important. Okay. Right, my friends. One by one, basic facts. Already you know, but still, right, rushing through it. When I talk about composition layer, crust, I know the fact that crust is the outermost composition layer, we know. And crust is largely, majorly made up of silica and aluminium, right? That's the reason crust, sometimes you call them as what? Sial. You call them as Sial. And the average thickness, don't take this fact very seriously because books to books, this fact slightly differs. Okay, but what is very, very important? There are two types of crust. What are the two types of crust? One, I call them as what? Continental crust. And two, I call them as what? Oceanic crust. Generally, what lies below the land, you call them as what? Continental crust. What lies below the ocean floor, you call them as what? Oceanic crust. Okay. So we have continental crust and we have oceanic crust. Okay. And there is one small exception. What is that small exception? There is a substantial part of continental crust also lies below the ocean floor, right? See, that is an exception. For example, continental shelf. The word itself says continental shelf. The word says continental slope. The word says continental rise. So all these words continent suggest they are continental crust. Okay, that is an exception. Otherwise, barring this exception, my dear friends, what I understand, what lies generally below or whatever lies below the land, right? That part of the crust, you call them as continental crust. Name itself says continent. And what lies below the ocean floor, barring these exceptions, right? The larger part of the ocean, you call them as what? Oceanic crust. There are two types of crust. Okay, right. Now, when I talk about the difference between these two types of crust, of course I know. Of course I know. What is that I know? Continental crust, that image itself said, continental crust is thicker, right? See, the image itself is saying, am I right? Image speaks more than 1,000 words, they say, correct? But when I talk about oceanic crust is thin. Continental crust is thick, but oceanic crust is thin, right? This is one aspect. Number two, continental crust is made up of light density rock. See, the average thickness is somewhere around, density is somewhere around 2.7. What is 2.7? It is 2.7 grams per centimeter cube. If I take 1 cubic centimeter of a rock, the weight of this rock will be somewhere around 2.7 grams. Whereas oceanic crust, it is 2.9 grams per centimeter cube. Even if you forget the value, what is that I should understand? I should understand that oceanic crust is denser. Oceanic crust is thin, but oceanic crust is denser. That is very, very important. Okay, right. This fact is very, very important. Continental crust is thick, accepted, but made up of light density granitic rock. Oceanic crust is thin, but made up of heavy density basaltic rock. Okay, right. And one more difference, my dear friends, let me tell you, this continental crust, generally they say it is more of Sial, whereas oceanic crust is more of Sima. Because later, somewhere we'll understand that entire oceanic crust today is made out of the magma that has come to what? The ocean floor from the mantle, right? So all the substance somewhere, whatever today we have in the name of ocean floor, that is created by the solidification of magma, which has ultimately came from what? Mantle. Mantle is more of Sima, right? Silicon and magnesium. That's the reason oceanic crust, we call them as what? Sima. And that's the same reason why exactly this oceanic crust is also what? Heavier, okay? Denser, right? Fine, my dear friends. And before we conclude, you know the fact, where exactly I'll be seeing the continental crust itself do not have uniform thickness. It'll be varying. Where exactly I'll be having maximum thickness, if you ask me, along the tall mountain chains. Along tall mountain chains. Example, Himalayas. And what type of mountain is Himalayas? Young-fold mountain. So not only here, wherever I have young-fold mountains, there all I'll be having a mountain route. It's something like a glacier, my friends, floating glacier, right? When talk about a floating glacier, normally we say the floating glacier, what you see outside the water is only 10%. What lies below the sea level or the level of the water is what? 90%. Very similar to it. When talk about tall mountains, what I see above the surface is only 10 to 15%, say 10%. And what extends as a mountain route is nearly 90%. So, wherever I have a tall mountain, the crust will also extend. That's the reason continental crust or maximum thickness of crust is felt along the tall mountain ranges. Whereas oceanic crust, and that too, oceanic crust is generally thin. In this thin oceanic crust, where exactly I'll be having, say, for example, very minimum thickness, if you ask me, along this oceanic divergence. Right? That's a place where exactly I'll be having this mid-oceanic ridge. I'll be having mid-oceanic ridge. Okay. So where I'll be having the maximum thickness, where I'll be having minimum thickness, both we have taken it. Okay, right. And my dear friends, one thing I understand, wherever this oceanic crust and continental crust goes for a convergence, right? Oceanic crust being heavy in density, oceanic crust will go for subduction. It will go for subduction. And subduction is the one which leads to destruction. Destruction of this crust, oceanic crust, continuously increases the magma pressure. And the magma pressure, when it increases, this magma will try to rise towards the surface of the earth, making the volcanic arc or giving rise to volcanic activity. Okay. So which crust generally goes for subduction, if you ask me? It is oceanic crust that goes for subduction. Right? Right, my dear friends. Now, and this is very, very important. See, for example, I know the fact. If somebody is asking me what exactly this crust is majorly made up of, because other name of crust itself, we call them as what? Sial. It means what? Silicon, aluminium. right? So we have a perception that the most dominating element in, say for example, crust is what? Silica and aluminium. But interestingly, if you ask me entire crust, which is the most dominating element is what? Surprisingly, it is oxygen. Oxygen occupies somewhere around 47%, followed by silica at the second place and aluminium at the third place. Ferrous at fourth place. Okay. So this fact, 1, 2, 3, 4 is very, very important. Though crust is largely, we call them as Cr. Interestingly, the most dominant element is oxygen, not the silica as such. Similarly, entire Earth, if I just take it, and somewhere if you ask me what exactly is entire Earth, the most dominating element of the entire Earth is what? Iron, 35%, right? 35%, more than 1/3 of this Earth is what? Made up of iron. Okay, right, my dear friends. Now, what exactly this crust is made up of, and entire Earth, that also we have an idea. And for namesake, if I just compare mantle, mantle is a middle compositional layer, we know, right? Mantle is primarily made up of silica and magnesium. That's the reason you call them as what? SEMA. Mantle generally extends between 60 kilometers and 2,900 kilometers. Otherwise, I can also say it extends between Moho's discontinuity to Gutenberg's discontinuity. This is another way of saying it. Average density is somewhere around 4.3 grams per centimeter cube. And what is very important, my dear friends, though mantle is not the thickest layer, but this is the largest layer. Largest layer both by mass and volume. Volume, 82% of Earth's volume is occupied by mantle, and somewhere around 67% of what? Mass. Okay. So either you calculate in terms of mass or you calculate in terms of volume, right? Mantle occupies the, say for example, the largest position in the Earth, right? And finally, when I talk about core, my dear friends, I know the fact that core is largely made up of nickel and ferrous, right? Nickel and ferrous, that's the reason you call them as what? Knife or nife. And core is rich in metalliferous metals, we know it. And I should understand that ferrous-rich core is the one which facilitates the geomagnetic property of the Earth. Why exactly Earth has a geomagnetic property? Why Earth behaves like a giant bar magnet, if you ask me? It is all because of ferrous-rich core. Okay, right. Right, my friends. And the density is somewhere around 11 to 13 grams per centimeter cube. See, crust. Even oceanic crust and continental crust, they had difference in density. But average, let me take it as crust is 2.8. Mantle is 4.3. Core is somewhere around 11 to 13. It means as I increase the depth, or as I increase, say for example, right, okay, with increasing depth, what happens? The density increases. Okay, right. If you ask me why exactly, what would have facilitated this arrangement? This arrangement is the outcome of sorting or differentiation, my dear friends. What is sorting? Sorting has not taken place today, way back, proto-Earth period, right? Say, for example, this gravity-based arrangement, you call them as what? Sorting or differentiation. Call them as sorting or differentiation. Okay? Right, my dear friends. Right. And let me also add one fact. If all the layers, if I just take it, if I calculate the average density of this Earth, the average density of the Earth stands at 5.5 grams per centimeter cube. And let me also tell you, with this value, right, Earth happens to be the densest planet in our solar system. All planets you take it, among them, the densest planet is what? Earth. Okay. And one more thing, see, I have just given you the value. The image is taken from NASA site itself. You can search it in Google, right? It will take you to NASA site. Now here, when I talk about, say, for example, this entire solar system, my friends, as of today, I have 8 planets. We have 8 planets in our solar system. These 8 planets can be divided into 4 plus 4. The inner 4 and outer 4. Technically, we call them as what? Inner 4, we call them as what? Terrestrial planets, right? These 4, we call them as what? Terrestrial planets. We call them as what? Terrestrial planets. Whereas the outer 4, Jupiter, Saturn, Uranus, and Neptune, we call them as what? Jovian planets. We call them as what? Jovian planets. You call them as terrestrial, and you call them as what? Jovian planets. Okay, right. Now here, one thing we understand. When I talk about this terrestrial and Jovian planets for the case, terrestrial planets are closer to the sun. Jovian planets are far away from the sun. This is one difference between them. Terrestrial planets are small in size. Jovian planets are large in size. This is another difference between them. Now, what is very, very important, my dear friends? These terrestrial planets are generally denser, whereas Jovian planets are, this is another difference. Okay. Terrestrial planets are smaller planets, but when it comes to density, they are very high. Okay. Jovian planets are larger planets, but when it comes to density, they are comparatively less. This is another fact what I can add it. Okay, right. So composition layer is very important, but in order to have the completeness, I am also discussing about the mechanical layers. Right, in terms of mechanical layers, my dear friends, right? The outermost layer, we call them as what? Lithosphere. And it's a solid layer. Average thickness is somewhere around 100 kilometers. But what is very interesting here, somewhere I understand, when I talk about entire lithosphere, the upper lithosphere consists of crust and lower lithosphere consists of upper mantle. It means, that's the reason I said, entire crust is lithosphere, but entire lithosphere is not crust because I have mantle here. Okay, only till 60 kilometers approximately what we have is what? Crust. Beyond it, what we have is mantle. And my dear friends, here, what I understand, light density, you increase the depth in Earth's interior, right? Light density, temperature also increases. You increase the depth, right? As you go towards the center of the Earth, notional, you cannot go. But somewhere I'm just saying, with increasing depth, like density, temperature also increases. Okay. So here I have just given you one chart for that also, right? We call this graphical representation as thermal gradient, or to be more precise, we call them as what? Geothermal gradient, right? Gradient. So what is this geothermal gradient? Somewhere we say, with increasing depth, what happens to the temperature? Temperature increases. But you find one pattern. What is this pattern? Though the temperature increases with increasing depth, the rate of change of temperature decreases with increasing depth. Very carefully if I analyze the statement. I said, with increasing depth, temperature increases. That is okay. However, the rate of change of temperature decreases with increasing depth. It means every layer the temperature is going to increase. That's okay. But where exactly the maximum rate of change of temperature, right? Maximum rate of change of temperature is experienced, if you ask me, right? It is at lithosphere. And where exactly the minimum rate of change of temperature is experienced, it is at core. So only one statement I said. With increasing depth, the temperature increases, but the rate at which the temperature increases, that decreases. Okay? Right, my dear friends. This is what the logic is. Okay. Right. Now, lithosphere, I have just taken it. And when I talk about asthenosphere, when I talk about asthenosphere, the layer which lies just below lithosphere, we have asthenosphere. Asthenosphere normally extends between 100 kilometers to 400 kilometers of depth. It's a layer of magma. We call them as a reservoir of magma or magma chamber. It's a partially molten layer. Sometimes you also call them as what? Semi-solid or substrata. The average temperature of this layer is somewhere around 1100 degrees centigrade or somewhere around 1100 degrees centigrade. But what is very important here, the point to be noted here, lithosphere is a solid layer and asthenosphere is a partially molten layer, right? It is a partially molten layer, my dear friends. And my dear friends, let me tell you, right? This lithospheric float over asthenosphere is the ultimate reason for the movement of plates, right? For example, we will be talking about continental drift theory. The very next topic we'll be discussing about continental drift theory. We'll be talking about plate tectonic theory. Why exactly? What is a plate if you ask me? The fragmented lithosphere, we call them as what? Plates. All right. So all this lithosphere divided into fragments and pieces, you call them as what? Plates. We call them as plates. Okay. And these plates, right, they'll be moving, having their own movement. That's what you call them as what? Plate movement or plate tectonic. Why exactly plates are moving, if you ask me? For the simple reason, lithosphere is floating over asthenosphere. Or I should put it this way. Why we have endogenic forces, if you ask me, I would say the causative factor is plate movement. What exactly is causing the plate to move? This is lithospheric float over asthenosphere. Tomorrow, if this asthenosphere is getting solidified, my dear friends, if it is getting solidified, these plates will not move. If the plates are not moving, there is no more orogenesis. There is no more new mountains that is being formed. There is no more volcanic activity. We'll not have any more earthquakes, no more tsunamis, no more ridge formations, right? It means somewhere I understand no more trench formation. Somewhere I understand, say for example, all endogenic forces will come to an abrupt halt. Okay. And what is the reason for having the endogenic force is all because of lithospheric float or asthenosphere. This word float is conceptually very important. Okay. Right. Right, my friends. Now, after talking about asthenosphere, just to conclude, mesosphere, solid middle mechanical layer, extends between 400 to 2900 kilometers of thickness. And of course, as I said, it's a solid layer. And when I talk about core, my dear friends, core itself, this is very important. When I talk about this core, we have two cores. The outer core is liquid and inner core is solid. And one more thing, let me tell you, see, we know the fact that with increasing depth, temperature increases. If you ask me why exactly the outer core is liquid, anybody can say the answer because of the temperature. Temperature is very high. So obviously speaking, it will be melting. And if you ask me what exactly is the temperature of the inner core, my dear friends, approximately to 6000 degrees centigrade. 6000, right? 6000 degrees centigrade. The similar temperature, what exactly is the temperature what we have in the outer surface of the sun and the earth's interior, both are similar, right? Both are similar, my dear friends. And now comes the question. 6000 degrees centigrade, how come this layer is solid? Because if you ask me what exactly is the melting point of rock, melting point of any rock, right? It may vary. Rock to rock, it may vary, but it is somewhere around 500 degrees centigrade to 600 degrees centigrade. This is the melting point of rock. Approximately at what temperature the rocks will be melting. 500 to 600 degrees. But this 500 to 600 degrees is at normal atmospheric pressure. Okay. And my dear friends, inner core, in spite of the fact 6000 degrees centigrade, if you ask me why exactly it is solid, it is all because of what? Pressure. Unimaginable pressure. This pressure is nearly 3.6 million times of atmospheric pressure. What we experience, right? Approximately, if you ask me what exactly is the average pressure, atmospheric pressure, it is 1013.25 millibars, we say, right? It is 3.6 million times, 36 lakh times. It is more. Okay, unimaginable pressure. So pressure is the one which makes this layer as what? Solid. Okay. So that is all about the internal structure of the earth, my dear friends. I feel this year internal structure of the earth is important in one way or another. Then this theory, continental drift theory, is a evergreen topic. Prelims or mains, who knows? Always there is a chance that they may ask a question, but the concept is very, very primitive. See, for example, always remember, my dear friends, this name of the subject what you are preparing for, it is called as general studies, right? Always remember this word called as general, right? General. So let's not get into the details of any theory. Okay. So where to have a demarcating line, we should know it. Okay. Now, what is this continental drift theory? See, for example, continents. Continents means assume that it is land. Okay. For the very first time, this is one of the first theory in geography which suggested that the continents or land were actually drifting from one place to another. Before that, we never had an idea that land was drifting. Mountain building formation, somewhere we used to explain the mountain building formation in a theory called as, with the help of a theory called as contraction theory. But contraction theory is today ruled out. So this is one of the first theory which we're talking about, the drift of continents from one place to another. Right? As I said, this theory, particularly this theory, continental drift theory, was propounded by this gentleman called as Alfred Wegener. He's a German climatologist. He's not a geomorphologist, he's a climatologist, a meteorologist. Right. Now, he presented his concept called as drift of continents. The text entitled Origin of Continents and Ocean. So his theory is also based on some of the pre-assumptions. As of now, the pre-assumptions are not needed for us. What is the theory? We should take it. In a nutshell, he strongly believed. See, what exactly prompted this gentleman to propound this theory, I'll tell you. There is a very close similarity when it comes to the shape of the coastlines of different continents. Very close similarity was there. So, having analyzed these similarities, and of course, Like a jigsaw fit, these continents, they actually fit with each other. Okay. The near complete fit of these continents strongly suggested, or at least Alfred Wegener felt, that all these continents, say for example, the southern, the continents largely which is confined to the southern regions as such, I'm just taking it. Okay. Almost you find that there is a near complete fit of these continents. Say for example, South America is fitting with Africa, right? Arabia is fitting with Africa. Antarctica and Africa, there is a fit. India and Antarctica, there is a fit. Antarctica and Australia, there is a fit. So large number of fit you experience, right? Or somewhere you witness this fit, right? Even randomly, if I just take any, say for example, this world map, my dear friends, somewhere if I'm just seeing it, I happen to see this fit, right? Largely, I happen to see this fit. Okay. So this fit suggests that all these continents, what is somewhere located in different parts of the world, strongly somewhere, it gives you a suggestion that these continents would have existed in as one single unit, and eventually they would have got divided or separated, right? So somewhere, using all these facts and of course based on some of the right evidences, Alfred Wegener somewhere started recreating the history of the earth, and accordingly concluded that, right, he strongly believed, he concluded that in the geological past, right, the geological past, only one continent was there existing. Entire Earth, only one continent was there. He was referring this continent as Pangaea. Supercontinent called as Pangaea. Okay. Till Carboniferous epoch, that is not needed. Pangaea. And this Pangaea initially got disintegrated, or I should put it this way, right? This Pangaea was all sides surrounded by another ocean called as Panthalassa. Right? It was somewhere surrounded by another ocean called as Panthalassa. And this Pangaea, my dear friends, somewhere it got initially disintegrated into two land masses. The northern land mass, you call them as what? Laurasia. And the southern land mass, you call them as what? Gondwana constituents. Right? It got divided into Laurasia and Gondwana constituent. So post-division, this land once again started drifting towards the equator and slightly towards the west. And the equatorial word movement and westward movement again made this continent to once again integrate with each other, and present day map of the world got evolved. See here, nutshell, if you ask me what exactly this theory is, remember once entire world had only one land, Pangaea. And Pangaea was all sides surrounded by this ocean called as Panthalassa, right? Only one land, only one ocean. Okay, one land and one ocean. And initially it got divided into two landmass. Which one? Pangaea. The northern landmass, you call them as Laurasia, or sometimes also referred as Angara land. Right? It is referred as Angara land. And southern landmass, you call them as what? Gondwana land. India is largely part of which landmass, if you ask me? India is largely part of this Gondwana land. Largely part of this Gondwana land. Okay? Right, my dear friends. So Angara land and Gondwana land. And post-disintegration, my dear friends. Post-disintegration, right? Somewhere it started drifting towards equator and slightly towards the west. And eventually, once again, it integrated with the continents of the world, and present day map of the world got evolved. Okay, and let me also tell you, when Pangaea got divided as Laurasia and Gondwana, between them, it also formed a sea. The sea, we used to refer it as Tethys Sea. If you ask me where is Tethys Sea today, largely Tethys Sea got modified. Modified into what, if you ask me? Modified into Himalayas. Not only Himalayas, Arakaniyama Mountains, Himalayas, Hindu Kush Mountains, Sulaiman Ranges, right? Caucasus Mountains. All this, if you ask me, it is modified versions of Tethys. Even Black Sea and Caspian Sea, we regard it as more a remnants of what? Tethys Sea. Even Mediterranean Sea, for that case, is a remnants of what? Tethys Sea as such. Okay, right. Fine, my dear friends. Now, what is a theory? We have an idea. See, most of the time, examination, what they may ask you is the evidence that is suggesting the drift of continents. See, for that, I should not take it as 1, 2, 3, 4 and all. I should not take it, right? Somewhere I should ask my rationality and I should somewhere get satisfied. Okay, fine. Is this evidence directly or indirectly talking about the existence of two divided land? Or say for example, somewhere today I have two divided land. Is this evidence directly or indirectly saying that these two divided land once existed as one single unit? I have to ask my question myself. Right? If the answer is yes, then yes, that can be taken as an evidence. In that way, right? What are the evidence which suggest that continental drift theory has taken place, if you ask me? Jigsaw fit of shape, process, structure. Shape, no need to explain it, because see, it is very visually, it is appealing. The different continents, the shape of the coastline you take it appears that near completely they fit with each other, right? See, if not all the continents of the world, at least these two continents. South America and Africa, my dear friends, like a jigsaw fit, right? And of course, it is also proved till the depth of 1,000 meters below the mean sea level, both the continents, they fit with each other. So it strongly suggests that these two continents would have existed as one single unit. That's what you call them as one jigsaw fit of shape. Process. For example, assuming that South America and Africa got divided by the process called as divergence. Of course, divergence. I know the fact wherever divergence is taking place, the commonest feature formed will be a rift valley. You may ask, where is that rift valley? Atlantic Ocean itself is a rift valley, right? And my dear friends, let me also tell you, along the rift valleys, what else I'll be finding is a block mountain. Do you have a block mountain, old block mountain here? If you ask me, answer is yes. We do have a block mountain here, right? Serra de Mantiqueira and Serra de Mor. Africa, we have a block mountain called as Adamawa Mountains, right? So block mountains right next to Rift Valley strongly suggest that this region would have been for divergence. See, what you are witnessing today, the eastern side of Africa, right, somewhere last 1.5 months, or just before 1.5 months, this was there in news. Nubian plate and Somalian plate goes for a divergence, right? Somalian plate is going for a divergence. Now here what happens, somewhere every news says that, okay, Africa is giving somewhere way to the formation of an ocean. Today it is not an ocean. Today is just you find a rift there. But tomorrow it can become an ocean. Okay. So somewhere I understand drifting will be resulting in a rift valley, and of course, eventually there may be a formation of a block mountain, but that's a very slow process. In our generation, or human race may not witness it for sure. Okay, right. So what is jigsaw fit of shape and process? We have taken it. What is this jigsaw fit of structure? I'll tell you, my friend. See, when I say structure, I'm talking about the structural similarity that exists between the different continents. For example, South America and Africa, if you believe that once it existed as a single unit, there should be some similarity between the rocks of South America and rocks of Africa. In that way, for example, we have some gold deposits here. We call them as a placer gold deposit, right? NCERT says the other way around. The example what I have given is other way around. Only thing is that we have a gold deposit. Source or destination of this gold deposit is identified in South America, whereas the source of this gold is identified from what? Africa. So when I say source one continent and destination another continent, strongly suggests that both this, right, say for example, source and destination in different continent means this gold deposits what you find in the place what I have marked it, we call them as Belem, right? This gold would have not been deposited in the recent times. This gold would have got deposited when both the continents would have existed as one single unit. I'm giving you one small example. Right? Similarly, my dear friends, what NCERT says, the gold deposits along the Ghana coast, you call them as what? Gold coast. Am I right? NCERT, what NCERT says, I'm saying. They say that actually they are sourced from South America. They say, according to them, they say destination is Africa, source is South America. Whatever be the case, one continent destination, another continent source means these continents would have existed as one single unit. Am I right? Mineral similarity. And not only mineral similarity, my dear friends, fossil similarity. See, n number of fossils they have studied. Okay. And say, for example, they find a kind of a continuity pattern of these fossils, right? across the continents, right? And all this, say for example, continuous regions, once they started assembling it, again, what they have ended up is a jigsaw fit. And again, the fossil continuity of the fossils in the different continent also suggests that all these continents would have existed as what? One single unit. For example, this Mesosaurus as a creature. It is a kind of a lizard, amphibian in adaptation, right? Almost say, for example, they were confined to Paleozoic era. Paleozoic era, the period when exactly the Pangea got divided, right? Today, we find Mesosaurus fossils only in two places. One is South American continent and African continent. What exactly they suggest, if you ask me? Simply they suggest that, right? It means they would have been confined to the confined landmass or the combined landmass. After becoming a fossil, they would have got divided and they would have, almost say for example, right now it is located in two different continents. Fossil similarity, right? Plays a very important role. Okay. So what is this jigsaw fit of shape, process, structure? That also we have taken it. And very important, paleoclimatic evidence. See, for example, this is in turn important. Climatic evidence may differ. For example, when I talk about Alfred Wegener, he himself has studied about this three regions by difference. India, Australia, and Brazil. See, today, India, Australia, and Brazil, all three countries you take it, they experience a tropical condition. Tropical means warm condition. But what is interesting? Geological past, they were experiencing polar-like condition. They were experiencing glaciated topography. They were highly glaciated. They were having glacial till or tillet. Glacial till or tillet means this glacial deposits, a kind of a glacial clay. You call them as what? Sometimes you call them as what? Moraines. Now, today it is there in tropical region, but in the geological past, it was experiencing polar-like condition. Then what we can think? We can also talk about what? Once we have come across something called as ice age, right? Pleistocene epoch, somewhere we had an ice age where the near complete earth was glaciated. But a clarification, even during the ice age, tropical regions were not glaciated. Only the temperate regions and the polar regions were glaciated. Okay, even assuming the tropical region is glaciated. What is very interesting, when India, Australia, and Brazil was experiencing glaciated condition, the same time, today's Siberia, part of Russia, was experiencing tropical-like conditions. See, today India, Australia, and Brazil experience tropical condition. Siberia experienced polar-like condition. But geological past, similar time, exactly opposite condition. If I take both the conditions together, the only convincing evidence is what? The movement of the continent, say for example, India, Australia, and Brazil would have been in polar region, and today it would have drifted to what? Tropical region. Siberian region in the geological past would have confined to what? Somewhere in the tropical region. Now it would have confined to what? The taiga and tundra belt as such. Okay, that's what the larger idea is. So, my dear friends, any evidence which suggests that continents would have been drifting or drifted, kindly take it as an evidence for the Alfred Wegener's continental drift theory as such. So, what is the theory we have seen? What exactly is the evidence suggesting that continental drift would have taken place? That also we have seen. See, otherwise, continental drift theory has its own fallacy that is not needed for us. Okay, right, my dear friends. So, that's all about continental drift theory. Okay, right. Now, moving on to the next theory called as plate tectonic theory. Again, see, why plate tectonic theory is important now, if you ask me, I would say it is all because of the African plate which has come in news. Okay, fine. Now comes the question, what do you mean by a plate? See, I know what is lithosphere. Outermost solid layer of this earth, we call them as what? Lithosphere. And I also know the fact that this lithosphere actually floats over another layer called as asthenosphere. It just floats over this layer called as asthenosphere. Now here, this lithosphere is a very thin layer and it goes for a constant movement. So given the fact, what happens? This lithosphere gets divided into fragments and pieces. That fragmented pieces of lithosphere is what we call them as what? Plate. I would say plate is nothing but what? Fragmented lithosphere. We call them as what? Fragmented lithosphere. Okay. You call them as a fragmented lithosphere. That's okay. Right. Fragmented lithosphere. And these plates, they go for a movement. Okay. And plate tectonic theory believes that any endogenic force is the outcome of this plate movement. Of course it is. Of course it is. Right. That's a reason. The other name for endogenic force. See, when I talk about endogenic force, what is endogenic force? Endo means within. Genic means genesis. When I say endogenic force, all the forces which has their genesis from inside the earth, you call them as what? Endogenic force. Okay, right. Now this is one. Okay, right, my dear friends. Right, what is endogenic force? We have an idea. Now see here, when I talk about endogenic force, right, my dear friends. When I talk about endogenic force, the other name for endogenic force, we also call them as what? Tectonic force. We call them as what? Tectonic force. Okay. When I say tectonic force, why exactly it took the name called as, it has a name called as tectonic force? It is all because of what? Plate tectonic. That's the reason you call them as what? Tectonic force itself. Okay. So it is all strongly believed that endogenic forces are the outcome of this plate movement or plate tectonic. Right. So plate tectonic theory is based on the principle that lithosphere is floating over asthenosphere and eventually moves under the influence of convective magma currents. So what is this convective magma currents? The continuous flow of this, say for example, magma, say for example in asthenosphere, we call them as what? Convective magma currents. Fine. So here, the entire lithosphere, my dear friends, it is divided into different plates. So based on the size, you call them as what? Major plates, minor plates, and micro plates. Right? You call them as major, minor, and micro plates. Okay. In that way, my dear friends, in that way, entire Earth is divided into 7 major plates, right? Somewhere around 20 minor plates and few micro plates, right? This minor plates, every minor plate is not important, but some of the minor plates are, yes, it is important. I'll tell you what are the minor plates, what is important. I'll tell you. Okay. Now here, major plates, 7 major plates. What are the 7 major plates? 1 Pacific plate, 2 North American plate, 3 South American plate, 4 African plate, 5 Eurasian plate, 6 India and Australia and the same plate called as Indo-Australian plate, 7 is Antarctic plate, right? All these 7 plates. Okay, these are the major plates. Now minor plates, my difference. Among the minor plates, what are very important? See, Californian plate. Name itself says California. So approximately I know where exactly is Californian plate. Cocos plate, very important. Cocos plate. What is very, very important is Nazca plate. Nazca plate. Okay. Nazca plate. Because the Nazca's plate convergence with South American plate is the one which has created the world's longest mountain called as Andes. Not only Andes, because I understand this is a conversion boundary between continental crust and oceanic crust. There you may also have the formation of what? Trenches. And this is also the world's longest trench called as Chile-Peru trench. So that way Nazca plate is very important, right? And so the other plates, what was there in news? 2 plates, Nubian plate, Nubian, and the Somalian plate. Both are important. See, Nubian and Somalian plate itself is part of African plate. Okay, it's very much part of African plate, my friends, but somewhere, right? So I should understand that they have a separate plate. For example, this is more like when I talk about African plate, Nubian and Somalian going for a divergence. It's more like an intra-plate divergence. Okay. Arabian plate name itself says where it is. Okay. Philippine plate also says where exactly it is located. Right? If at all, if you want to remember, kindly remember this Caroline plate. Caroline and Bismarck. So, slightly what the name may not suggest you, somewhere if you want to remember separately. You remember Caroline? You remember Bismarck? You remember Nazca? You remember Cocos? Even Caribbean plate says where exactly it is. Scotia, I don't feel it is so important. Okay. So only 4 plate if you want to remember extra, you kindly remember it. Right. Now, the entire lithosphere is divided into these many number of plates, major and minor plates. And of course, I understand that these plates goes for their own movement as such. They go for a movement. Okay. And when I say they are going for a movement, my dear friends, movement. The plate boundaries or the margins are the one where 2 or more plates will be interacting with each other. And these boundaries are the place where exactly I'll be having the confinement of these endogenic forces. Right? So any endogenic force, normally you take it, and if you ask me where exactly, locationally, where exactly they'll be confined to, they'll be confined along the plate margins as such. Either you call them as plate margin or you call them as what? Plate boundary. An entire plate tectonic theory, my dear friends, entire plate tectonic theory, they somewhere analyze this plate boundary. They simply analyze this plate boundary. Okay, right. Right, my dear friends. Now we are also going to analyze this plate boundaries as such. Okay. In that way, I have also given you the list of plates, at least the major plates. The size and all it is not needed, but I have just given you an order, right? An order. What is this order if you ask me? This order is descending order in size. So among the 7 major plates, which is the largest place if you ask me, be it the ocean or the plate, Pacific plate is the largest. Okay. Among the major plates, South American plate is the smallest. Just for your right. Just the factual information I have just added. Okay, right. Now, I said all endogenic forces confined to this plate boundaries. And majorly, how many different types of plate boundaries are there if you ask me? Majorly, there are 3 different types of plate boundaries. One, it's all about the combination. America. Plates are moving and 2 or more plates are interacting with each other. If 2 plates move towards each other, if they start colliding with each other, that boundary we call them as what? Convergent boundary. They start moving away from each other, of course, we call them as what? A divergent boundary. And somewhere if it slide past each other, neither convergent nor divergent, but still slide past each other, you call them as what? Transform boundary. So at any given point of time, right? Or I could say, right, there are 3 different types of boundaries normally what we have: convergent, divergent, and transform boundary. These are the 3 different major types of boundary. Okay. See, third transform boundary also, I will say that it is more an exception. My understanding should be largely with convergent and divergent, because today transform boundary, though I say it is a transform boundary, it is more similar to the nature of divergent boundary. The type of stress induced will be different, right? Divergent boundary, what will be having is what? Normal tensile, means normal tensional stress or tensile stress will be there, right? When talk about transform boundary, my difference, what you will be experiencing is a shearing stress, right? Convergent boundary, what I'll be having is a compressional stress. The kind of the stress will be different. But whatever be the case, today, very practically speaking, transform boundary behaves more or less similar to that of divergent boundary. Why I am saying similar in the sense, whatever is the feature that is formed along the transform boundary, or those features which is also formed along divergent boundary, right? So I should know that there exists a transform boundary, exists a third type of a boundary called as transform boundary. But my larger understanding should be around this convergent and divergent boundaries. Okay, right. Now here, for understanding what we have to do, my dear friends, we have somewhere classified this boundary into 3 types: convergent, divergent, and transform boundary. They have their own meaning, right? Say, for example, they have the other names also. For example, convergent boundary, you call them as a destructive boundary. What is the meaning of destructive here? I tell you. Whenever the rock becomes magma, rock gets destructed. We call them as what? Destruction. So whichever boundary where the rock is becoming magma, the rocks are getting destructed, you call them as a destructive boundary. Right? If rock becoming magma is called as destruction, then what exactly I may mean by construction? Magma becoming rock, I call them as what? Construction. Wherever the solidification of magma takes place, my dear friends, right? Wherever the solidification of magma takes place, they're all that boundary, we call them as what? Constructive boundary. So divergent boundary, we call them as what? Constructive boundary. where normally the solidification, new crust will be formed. Convergent boundary is the place where old crust will be destroyed. And divergent boundary is the place where new crust will be formed. And most of the time, this old crust or new crust, most of the time it will be oceanic crust. Right? Because what gets destructed is only oceanic crust. Because only oceanic crust will go for subduction, and subduction will result in what? Destruction. Right? Oceanic crust may result in destruction, my friends. Okay. And when I talk about construction also, by default, see, we do have construction as an activity along. Maybe the lava plateau is also an outcome of constructive boundary. I'm not denying the fact. But barring that exception, how the new oceanic crust is created? Oceanic divergence. Right? Okay, fine. So what is convergent? What is divergent? Yes, we have an idea. We'll not even discuss about transform boundary because transform boundary is a minor example. Now here, my dear friends, when I talk about convergent boundary, two plates that is converging towards each other, you call them as what? Convergent boundary. And I know the fact that crust itself is of two types. Type of the crust makes the type of the lithosphere. If that is the case, my dear friends, convergent boundary itself, I can have three types of convergent boundary. What are the three types of convergent boundary? See, one side I can have oceanic crust and continental crust going for a convergence. You call them as what? Ocean-continent convergence. Another example, continental crust and continental crust may go for convergence. You call them as continent-continent convergence. And the third example, both sides I can have oceanic crust going for a convergence. You call them as what? Ocean-ocean convergence. That's what I have written it here. Okay. Three types of convergent. Ocean-continent, continent-continent, ocean-ocean. Similarly, when I talk about divergent boundary, my friends, what I understand, divergent boundary, only similar type of rocks will get destructed. For example, if continental crust is getting divided, right? Both sides I'll be having continental crust. I call them as what? Continent divergence. If both sides I have oceans, right? Oceanic crust and oceanic crust going for a divergence, I call them as what? Ocean divergence. See, any ocean divergence would have started as continent divergence and eventually would have become what? Ocean divergence. Right? For example, I'll put it this way. For example, just now we have taken this, right? If you ask me, okay, give me one example of this ocean divergence. Divergence in the middle of the ocean. See, mid-Atlantic region. You have this very famous mid-Atlantic ridge here. Okay. Now see, when talk about the middle of the ocean, North American plate and Eurasian plate going for a divergence. South American plate and African plate going for a divergence. See, today, South American plate and African plate divergence, if you ask me, it is more like ocean divergence. But it started as continent divergence, and today it is more like ocean divergence. Okay, right. So that's what even this image says, right? What starts as continent divergence may tomorrow become ocean divergence. That's what, again, correlated. News what they say. The split of Africa may give rise to new ocean. Not today, tomorrow. Tomorrow means geological tomorrow, where you and me will not be there. Okay. Right, my dear friends. Now, what I have just done, this convergent boundary I have divided into three types. Divergent boundary I have divided into two types. See, we practically speaking, ocean-continent divergence do not take place because largely understanding says divergence will be happening only with a similar type of rock. A rock will get split open, it will be going for a divergence. If that is the case, both sides I'll be having only similar type of rock. Ocean divergence, ocean-continent divergence is not possible. If you are not satisfied with the concept that it is not possible, you can take it that today we don't have an example. Okay. So totally, transform boundary is a small boundary, will not subclassify it. So all types of boundaries, if I just take it, right, these are the all types of boundaries, right? Three boundaries for greater understanding, you can make it as what? Say, for example, 6 different types of boundaries. 3 convergent, 2 divergent, and 1 transform boundary. The only thing is that I have to largely understand what are the different features I'll be having it, right? First, I'll start with this ocean-continent convergence. See, this ocean-continent convergence. The classical example of this ocean-continent convergence, right? Classical example. Just now I said Nazca plate and South American plate. One side ocean, one side continent. To some extent, I can also take Pacific plate and North American plate, barring few exceptions here and there. Eurasian plate and Pacific plate. Eurasian plate and Philippine plate is also kind of an example where continental crust and oceanic crust is going for a convergence. It's kind of an example. But American coastline is the classical example. It means the larger example, my friends, one of the classical example of this destructive boundary, right? Ocean continent convergence, I can take it as circum-Pacific belt. All sides of Pacific Ocean. All sides of Pacific Ocean. See my difference. All sides of Pacific Ocean, it is a ocean continent convergence. Continental crust and oceanic crust is going for a convergence. And wherever convergence is taking place, there all I'll be having what? Fold mountains. And I know the fact, wherever continental crust and oceanic crust is going for a convergence, oceanic crust being thick will be going for what? Subduction, right? And this subduction will be resulting in the formation of a trench. Wherever subduction is taking place, there all, if the subduction is visible, this visible zone of subduction, you call them as what? Trench. And the subduction leads to destruction, right? Destruction results in increased magma load, and this increased magma load will be resulting in what? This volcanic activity also. Rising volcano or rising magma will result in volcano, the land side, and sometimes, right, volcanic island in the ocean floor. Okay, now one thing I understand. Wherever continent and ocean is going for a convergence, what all I may find here? Fold mountain, volcano, volcanic islands, even volcanic islands, you forget about it here, right? I may have fold mountains, volcano, and trenches. Classical example, my friends, when I talk about Nazca plate and South American plate going for a convergence, see, do you have a trench here if you ask me? Yes, the world's longest trench. Do you have the mountain here if you ask me? The world's longest mountain, Andes. The world's longest trench, Chile Peru trench. Do we have volcano if you ask me? Yes, we have volcanoes like Mount Chimborazo, Mount Cotopaxi, Mount Cerro del Salado, plenty of volcanoes are there. Okay, and one more thing, what is the example we have taken? We have taken the example of circum-Pacific belt. And my different circum-Pacific belt is the single largest continuous destructive zones of the world. Nearly it extends for 40,000 continuous stretch of extension. 40,000 kilometers of extension. Right? Continuous extension. The periphery of the Pacific Ocean. Right? And my dear friends, this region has lot many number of volcanoes. One fact, old fact says, there are about 453 active and dormant volcanoes. Wikipedia now it has changed the information, but older information says 453 active and dormant. Extinct is not counted. Or simply I can say large number, thousands of volcanoes are there in this region. That's the reason this region is very popularly called as what? Pacific Ring of Fire. It is called as Ring of Fire. Fire means what? Volcano. Alright. Fire signifies volcano. And this region alone, my dear friends, somewhere accounts for more than 80% of world's volcanic population. 80%. Right? And nearly 90% of large earthquakes are confined to this region. I'm not saying 90% of earthquake. I'm saying what? 90% of world's large earthquake, right? Including, I talk about Chilean earthquake of 1960, my dear friends, right? Chilean earthquake of 1960, Chile. This is the largest earthquake that what we have recorded in our human history. Magnitude of somewhere around 9.5 magnitude. What, say for example, according to us, this is the largest earthquake what we have recorded. Okay. Right, my friends. And this region also has lot many number of what? Trenches. See, region known for trenches, known for earthquake, known for volcanoes. Alright, of course, it is also known for what? The continuous stretch of fold mountains, Pacific Ring of Fire. One small observation. When I say Pacific Ring of Fire, name says Pacific Ring of Fire. It means periphery of the Pacific Ocean. But what is interesting and the point to be noted here, is this Pacific Ring of Fire confined only to Pacific Ocean? If you ask me, no. Pacific Ring of Fire marginally extends into Atlantic Ocean and they marginally extends into Indian Ocean also. Pacific Ring of Fire extending in Indian Ocean, my dear friends, Indonesia, East Indies, am I right? And Atlantic Ocean, Caribbean Islands, West Indies. Okay, so that's the reason we say Pacific Ring of Fire. Towards the east, it extends till West Indies, and towards the west it extends till East Indies, that is Indonesia. So the point what I'm trying to make, Indian Ocean also you have the presence of Pacific Ring of Fire. Atlantic Ocean also you have this Pacific Ring of Fire. Not necessarily Pacific Ring of Fire is confined only to the Pacific Ocean as such. Okay, right. So ocean and continent convergence, you experience all endogenic features and process, including volcanic activity. We have fold mountains, we have trenches, we do have volcanoes, we do have volcanic islands also. Okay, right. Right, my dear friends. Now, earthquake. This region is also confined to earthquake, already I said. So consolidated. All features be taken. On the side of the ocean front, we have trenches, we may have islands. On the continental front, we may have fold mountains and we may have what? Volcano. And not only here. Every plate boundary, I'll be having an earthquake. So what is an earthquake? Once we talk about earthquake, we'll understand it better. Okay? Right. Right, my friends. Now talking about the second type of convergent boundary, continent and continent converging. It means both side the convergence of continental crust is taking place. For example, if you ask me, okay, give me a classical example of this boundary. That is Eurasian plate and Indo-Australian plate where it is converging, right? Himalayas. Himalayas is a classical example where continental crust and continental crust is going for a convergence because both are similar in density. Both are very light. They don't go for convergence, or excuse me, they do not go for subduction. Because there is no subduction, we do not have volcanoes. There is no trench, obviously speaking. When ocean is not there, we will not have trench. But what is very important, we will not have volcano. Okay. The only feature what we'll be finding is fold mountains. And let me also tell you, any boundary you take it, they are susceptible to earthquake. And particularly when I talk about young fold mountains, these young fold mountains are highly susceptible to earthquake, my dear friends. They're highly susceptible to earthquake. See, why we say it is highly susceptible to earthquake, I'll tell you. Because fold mountains are the place where exactly I'll be having shallow earthquakes. For example, Turkey, I can take it with Caucasus Mountains. Caucasus Mountains being very close to it. Influence Turkey. Even when I talk about, say, for example, earthquake-prone zones in India, most of them, they're confined to what? Himalayan region. The world's largest earthquake, what is recorded in Chile, that is associated with what? Andes Mountains. All the names what I have taken, Turkey earthquake, influence of Caucasus Mountains. Himalayan region, highly prone to earthquake, Himalayas. World's largest earthquake that was recorded, Andes Mountain. All these are young fold mountains. Any young fold mountains, my dear friends, they are highly susceptible, vulnerable to what? Earthquakes. Kindly remember it. Okay, right. So Himalayas is one of the young fold mountains in the world which do not have volcano. Okay, very prominent example because except Himalayas, any other fold mountains you take it, Rocky is known for volcanoes. Am I right? Even say for example, if not Alps, the region around the Alpine Cordilleras is known for volcanoes. Andes is a fold mountain, right? Over and above Andes, we have plenty of volcanoes, but Himalayas, we do not have volcanoes as such. Okay, right. And coming to the last type of convergent boundary, it is ocean-ocean convergence. And talk about ocean and ocean going for a convergence. Philippine plate and Pacific plate, classical example, right? I'll show you this Philippine and Pacific plate, right? Philippine plate and Pacific plate, my difference, they are going for what? A kind of a convergence. Both are heavy oceanic crust. Since both are heavy oceanic crust, my difference, what I understand, both together, they go for what? Subduction. And here also we'll be having the formation of a trench. And the trench formed here, my dear friends, the trench formed here, somewhere I understand. Okay, the trench formed here will be more deeper as such. Okay, the trench will be more deeper in general, right? It will be deeper. And finest example, where this Philippine trench and Pacific trench is going, sorry, Philippine plate and Pacific plate is going for a convergence, my difference. This is the place where you have the deepest trench of the world. And this deepest trench of the world, we call them as what? Marianas Trench. Right? This is the place where you have this deepest trench of the world, right, located. Right. Now here, all these convergent boundaries we have taken. Now coming to divergent boundary. Among the divergent boundary, which is the most commonest divergent boundary? Commonest divergent boundary is oceanic divergence. That is ocean-ocean divergence. Both sides I will be having oceanic plate. See, African plate and South American plate, North American plate and Eurasian plate, all are going for divergence. Nazca plate and Pacific plate, right? Pacific plate and Antarctic plate, African plate and Antarctic plate, Indo-Australian plate and African plate, Indo-Australian plate and Antarctic plate. It means any boundary in the ocean, by default, it happens to be oceanic divergence. And oceanic crust being very thin, my dear friends, very easily it gets opened up. When it very easily gets opened up, the magma somewhere very easily rises to the surface, right? Slowly, steadily, when the magma starts growing, right, it forms a mountain-like structure. This is what you call them as what? Mid-oceanic ridge, sometimes also called as submarine mountains. And these submarine mountains may emerge above mean sea level to form an island. Okay. So where here, the default feature, what you'll be finding, wherever oceanic divergence is very common, there you'll be finding what? Mid-oceanic ridge. Ridge emerging above mean sea level, I'll be having this formation of islands. And these islands are volcanic islands, sometimes also referred as hotspot islands. And my dear friends, if these islands are very large in size, I may also have the presence of volcano there. Okay, right. Right, my dear friends. It's all about oceanic divergence, the most commonest divergent boundary in the entire world. Now talking about that plate which is there in news. Am I right? In news, for example, what was there in news? The Great Rift. Africa's splitting plates could give birth to a new ocean, but with consequences. Is what it is there in news. Okay, right. Right, my dear friends. Now here, we talk about this continental divergence. Continental divergence, the classical example, it is an intraplate divergence of African plate, my dear friends, where Nubian plate and Somalian plate, both are African plate, right? That part of African plate, you call them as Nubian and Somalian plate, they go for a divergence. And any divergence, what is the default feature you will be having? The default feature, what I will be having is a rift valley. Do you have a rift valley here? If you ask me, obviously yes. Right? The world's largest existing rift valley of the world. Great African Rift Valley. Do you have a block mountain here? Obviously yes. Mutumba. Convergent boundary, I'll be having a fold mountain. Divergent boundary, I'll be having a block mountain. Then see, like oceanic crust, continental crust can also completely open up. If it is completely opening up, the magma can still come to the surface, spreads horizontally, spreads for a longer or larger distance, covers a larger area, and eventually forms what? Lava plateau. Right? It may form a lava plateau. Correct? In that way, you may also have a lava plateau. Ethiopian highland is a classical example of a lava plateau. Right? Then, my dear friends, when I talk about, say, for example, you do have volcanoes here. See, wherever magma can come to the surface, always I can have what? Volcanoes. Right? We do have volcanoes here, very popular volcanoes like Kilimanjaro. Kilimanjaro is a very popular volcano. Right? Kilimanjaro, Mount Kenya, these are some of the very popular volcanoes what you have it. Okay. Right, my dear friends. Now, okay, fine. So the very important volcanoes of the world also we have just taken it. And let me tell you, my dear friends, when I talk about volcano, earthquake is universal. We have a plate boundary, earthquake is eventual. If you have a plate boundary, volcanic activity is common. One exception is there. What is that exception? I'll tell you. Okay. So this intraplate divergence of Africa, I feel it is important. One somewhere I felt internal structure of the earth, particularly Gutenberg's and Lehmann's discontinuity, I felt it is important. Similarly, this Nubian plate and Somalian plate also, I feel it is important. Okay, right. Right, my dear friends. Now, it's all about divergent boundary. And talk about transform boundary, my dear friends. I understand transform boundary today behaves more like a divergent boundary. The transform boundary happens to be in the land It behaves more like continental divergence. The transform boundary happens to be in the ocean. It behaves like oceanic divergence. In that regard, one of the most prominent transform boundary of the world, Californian plate and North American plate going for a kind of a transformation. Californian plate. Where is Californian plate? See, this peninsula of Mexico, we call them as what? Californian Peninsula. This Gulf in the western side of Mexico, we call them as what? Californian Gulf. And the state in USA, we call them as what? California. So where is Californian plate? Very simple, all California. Californian state, Californian Gulf, Californian Peninsula. Okay, right. So California. So California and North American plate, almost they go for a kind of a transformation. They go for a transformation. Now, what are the features? I told you. The similar feature what we have along a divergent boundary. Divergent boundary, what all we had? Rift Valley. We do have a Rift Valley here, San Andreas Fault. 1,200 kilometers of continuous Rift Valley. We do have a block mountain here, very important, Sierra Nevada. We do have a lava plateau, flood basaltic province like Columbian Plateau. We do have volcano like Mount Shasta and Mount Whitney. Similar feature. Okay. So all the feature, if I consolidate my difference. Right? Convergent boundary, if you take it, the maximum number of features is what? This one. Ocean side, I'll be having a trench, islands. Land side, fold mountain and volcano. So wherever I have fold mountain, there all I'll be having volcano. But what is an exception? Himalayas is an exception. Himalayas is one of the few mountains in the world, fold mountains in the world, which is not associated with volcanic activity, right? Which is not associated with volcanic activity, right? Right, my dear friends. Now, having said this, divergent boundary, oceanic divergence, very common. Oceanic divergence, oceanic crust being very thin, opens up. We have the formation of mid-oceanic ridge. If mid-oceanic ridge grows above mean sea level, it becomes an island. The island becomes very large. You can also have volcano. What about continent-continent divergence? Rift Valley and block mountains, very common. Horst and Graben topography. The complete crust opens up, it forms a lava plateau. If the magma can come to the surface, it may also form volcano. And whatever feature I have it along continental divergence is a similar feature I'll be having it along what? Transform. So one thing I understand, every place, what you'll be having is what? Volcano. Okay. The only mountain, only place where you do not have volcano is what? Continent-continent convergence. Here I have not written it. Ocean-ocean convergence also, when I talk about island, these islands are volcanic islands. Okay. Almost volcano is universal. But one thing I understand, wherever I have a plate boundary, except one, I'll be having volcanoes everywhere. But one difference is there. When I talk about volcanoes along convergent boundary versus divergent boundary, this volcanic activity along convergent boundary will belong to intense type. They are very intense. Whereas volcano along the divergent boundary will generally be what? Quiet type. Quiet type in the sense, the rate at which the magma rises may not be so strong. That's what the idea is. Okay. Right, my dear friends. Now, right, we have done with plate tectonic theory. Plate tectonic theory itself has given us an idea about earthquake and volcanic activity. Now, this volcanic activity, earthquake and tsunami, we'll be doing it separately. Then going to the fourth topic of the day. Totally, we have 7 topics. Yeah, right. 7 topics. Volcanic activity will be 4. Earthquake will be 5. Tsunami will be 6. Rock cycle will be 7. Volcanic activity, my dear friends. What is volcanic activity? All set of process that facilitates the magma to move towards the surface of the earth from asthenosphere. We call them as what? Volcanic activity. It is a rise of magma. Simply the rise of magma. This rise of magma, we call them as what? Volcanic activity. Right? In that way, my dear friends. In that way, here, if you ask me, okay, what is the potential? See, volcanic activity is more like a vent mechanism. It tries to releases that extra pressure of asthenosphere. But here, what is the landforms that generally they are formed out of this volcanic activity, if you ask me? The landforms that is formed. It can form a lava plateau, right? It can form volcanoes. Volcano is a mountain. It can form islands. And we do have intrusive landform features. What is this intrusive landform feature? I tell you, right? So what is volcanic activity? Volcanic activity is all about an attempt of magma and coming towards the surface of the earth. From where? Astronosphere. Okay. If this magma successfully reaches the surface of the earth, we call them as what? Extrusive volcanic activity. Right? Reaching the surface of the earth. If it is not reaching the surface of the earth, somewhere if it is getting solidified well within the surface of the earth, we call them as what? Intrusive volcanic activity. This extrusive type is the one which generally forms landforms, not the intrusive type. But what is intrusive today may not be intrusive or say for example lying below the surface always. Sometimes there is n number of chance that they can get exposed on the surface. If the intrusive volcanic features are getting exposed on the surface, that is what we call them as what? Intrusive landform features. We call them as what? Intrusive landform features. Okay. And my dear friends, this extrusive volcanic activity is very important here. This extrusive volcanic activity itself, we have two types. One is fissure type and two is central type. What is fissure type and central type? I'll tell you, my dear friends. If the magma is flowing through multiple openings, see here, multiple opening, we call them as what? Fissure type. If the magma is flowing through one central opening, one single point of ejection, we call them as what? Central type. Okay. Multiple opening, we call them as fissure type, and one central point, we call them as what? Central type. So normally, the central type of volcanic activity, my dear friends, will be resulting in the formation of volcano, whereas fissure type will be resulting in the formation of what? Lava plateau. Lava plateau. What you see here is more like a lava plateau, right? It's more like a lava plateau. Okay, right. You have this fissure type, and say for example, you have this lava plateau as such. Okay. Now, few words about lava plateau if I just take it. Lava plateau, I understand. Sometimes you call them as what? Flood basaltic province. Basaltic, this word basaltic is the right. Any feature that is formed out of solidification of magma will be a basaltic feature. And if that is the case, this basaltic province itself will be what? Kind of igneous rocks. Later, today's end of the class, maybe another, say for example, 20 minutes, we'll be opening this topic called as this rock, types of rocks, right? There we'll be talking about these igneous rocks. So basaltic rocks. Any rock which is basaltic means made out of magma. That's basaltic. Okay, right. And where all I'll be having this lava plateau, if you ask me, lava plateaus you may find along both continental divergence as well as what? Transform mode. Every place. For example, when the crust opens up, simple, the magma comes up. Right? See, the crust is opening up. Right? Something like this, the crust is opening up. Once the crust opens up, the magma comes out, spreads in the larger distance. Horizontally it spreads and forms one lava plateau. Okay? Right, my dear friends. Now, what is most commonest type of volcanic activity is the central type. Central type normally results in the formation of what? Volcano. Right? It somewhere results in formation of volcano. In that way, my dear friends. We talk about fissure type, my dear friends. Fissure type we have done with central type. The central type normally results in volcano. Right? And this volcano can be classified either based on frequency or based on intensity. See, frequency means how frequent it is erupting. Somewhere if this magma is erupting now, if the vent is open, we call them as what? Active volcano. If the vent is temporarily closed and any time in the near future if it can erupt, you call them as what? Dormant volcanoes. Today it is sleeping, tomorrow it can awake. Somewhere it can get activated. Either you call them as dormant or you call them as what? Sleeping volcano. The third type of volcano, we call them as what? Extinct volcano. Over. Rest in peace. Am I right? Right. You call them as what? Extinct volcano. No more volcanic activity. You call them as what? Extinct volcano. Right. And see, today, when I talk about India, India has two volcanoes. Only two volcanoes. Only two. Wikipedia says plenty of things. Wikipedia says even Deccan Plateau is a volcano. It's not even Deccan Plateau. They should have given us Deccan Trap. Change it if it is possible. They talked about Doshi Hills, Tosham Hills, Dinodar Hills, right? Haryana and Gujarat, they have given that volcanoes there. They are not volcanoes, they are volcanic feature which formed during Paleozoic, right? They have talked about, say, for example, Loktak Lake of Manipur as volcano. Even they have talked about Baratang, right? Mud volcano in Andaman and Nicobar. That is also not a volcano. It is strongly believed. Baratang volcano is more like mud volcano. That is okay, but it is more because of biotic action, not because of rising magma. So today, as a volcano, India only has two volcanoes. One is Narkondam, right? I'll put it so, right? Barren, Barren volcano and Narkondam volcano. Both are islands. Barren Island is also a volcano. Narkondam Island is also a volcano, right? Both are confined to Andaman Islands. Andaman groups. Both are confined to Andaman groups. Okay, right. Now, when we talk about present state, today, Barren volcano is an active volcano, whereas Narkondam is dormant or sleeping. If you are referring your atlas, my dear friends, in your atlas, Narkondam is given as extinct. But Geological Survey of India in December 2020, they have classified Narkondam as, right, dormant volcanoes. Okay. GSI, once you search it in their official website, type it as, say, for example, Narkondam type of volcano, Geological Survey of India. Their official website page itself says that it is an example of dormant volcanoes. But most of the atlas, it is given as extinct volcano. That correction you can somewhere note it down. So India, clarification, only two volcanoes. Barren is active. It was active since 2017. 2017 it has become active. Ever since 2017 it was active. Right? No. Then we had Narkondam, which is dormant today. Now, volcanoes can also be classified based on intensity. Intensity in a sense, how intense is volcanic activities? How intensely, say for example, violently the magma is rising. In that way, we differentiate between quiet and intense. See, quiet type versus intense type. Intense type, we find it along destructive plate boundary, right? Whereas quiet type, we find it along what? Constructive plate boundary, right? Constructive. In that way, Hawaiian is quietest type, where oceanic divergence. Strombolian type is continental divergence. Vesuvian and Pelian, I'll be having along destructive boundary. And Pelian is the most intensive type of volcanic activity what we have recorded. Pelian is not a separate type. Intensified Vesuvian, we call them as what? Pelian. Okay. Going for individual magmas and all, it is not needed. And let me tell you, my dear friends, any volcano you take it. Every volcano, they have some commonality. What is common, right? What is common if you ask me? Every volcano will be having different layers. Different layers. That's why this volcano itself, we call them as what? Accumulated mountain. Layer by layer, this magma is getting accumulated. Right? It is getting what? Accumulated. You call them as what? Accumulated mountain. Right? So somewhere, every layer, they get added during one episode of eruption. If one volcano has 5 layers, means at least 5 times this volcano would have got erupted. That's the meaning. Okay? Right, my dear friends. Similarly, any volcano you take it, you will be having a well-defined path for the movement of magma to reach the surface of the earth. You call this as pipe. And the opening up of this pipe, we call them as what? Vent. See, somewhere, I told you that volcanoes can be classified as active, dormant, and extinct. When the vent is open, you call them as what? Active. When the vent is temporarily closed, we call them as dormant. When the vent is permanently closed, we call them as what? Extinct. And what is very important, my dear friends, a unique feature, I should say it is more like a trademark feature, right? Any volcano you take it at the apex, you may have a depression. And this depression, you call them as what? Crater. You call them as what? Crater. Okay. So these are some of the commonality what every volcano has. Okay. And my dear friends, every volcano you take it, they'll be having some ejected matter. Whenever I say any volcano is active, it means something should be ejected. That ejected matter itself can be magma. Correct? This magma, generally we have two types of magma. One we call them as basic magma. Excuse me, right? You call them as basic magma, and 2 you call them as what? Acidic magma. What is basic magma? Of course, it is classified based on the pH value, right? Based on the pH value, but whatever it is the case, when I talk about basic magma, normally basic magmas are the one which has very less silica content. Because the silica content is very less, the viscosity, it's more like the thickness of this magma, right, will be very less. Because of this fact, the mobility of this magma will be very high, right? As a case, normally lava plateaus will be the outcome of this basic magma, right? See, basic magma will be flowing like a flood, very fluidic in nature. That's the reason lava plateaus are sometimes called as what? Flood basalt, right? Why it is called as basalt means any igneous features, volcanic feature, you call them as what? Basalt. Why flood? Because it is made out of fluidic magma. It is made out of basic magma. That's the reason, right? Excuse me. Right. Now, acidic magma, my dear friends, the silica content will be more, viscosity will be more, as the case visco means mobility will be less. So normally most of the volcanoes are formed out of this acidic magma. See, I have kept a star mark and I used this word called as most. It means I have not included this word called as all. I have included this word called as most. Okay, very important point. It means we do have a volcano called as basic volcano. Hawaiian volcanoes, Mount Mauna Kea and Mount Mauna Loa, we call them as what? Shield volcanoes or basic volcanoes, because they are more made out of basic magma. Okay, right. Now, my dear friends, when I talk about some of the commonest gases that is being emitted or ejected, right? So the commonest gas, right? What are the commonest gas that is getting emitted? I'll tell you, my dear friends. Most commonest gas emitted is what? Water vapor. And that's the reason, after any volcanic activity, what is very common, normal is what? Heavy spell of precipitation. Because this water vapor goes for condensation, it will be resulting in what? Precipitation. Apart from that, you may have also what? Carbon dioxide that is getting emitted. And along with that, you may also have what? Sulfur dioxide. See, I told you, release of water vapor results in what? Precipitation. And not only water vapor, my dear friends, it is also sulfur dioxide. And the combination of the same, it can give you, somewhere it can result in what? Acid rain. Right? This rain is not a common rain or a normal rain. What you may experience is what? One acid rain. Right? Right, my dear friends. Okay. And one more thing, along with the gas, kindly also include this etc. Because what I have included is what? The most important three. Along with this, we may also have some solids that is getting ejected. Volcanic ash, burnt material, pyroclast, small igneous pieces of rocks, and tephra. Right? Tephra is a combination of both. Volcanic ash and pyroclast put together, you call them as what? Tephra. Right? So these are some of the solids that gets emitted during any volcanic activity. Whatever gets emitted or ejected, that volcanic activity, you call them as what? Active volcanism. Right? Right, my dear friends. And finally, already I discussed about it. When I talk about the types of volcano based on intensity, the very quiet being Hawaiian, quiet but not so quiet, you call them as Strombolian. Intense type and the most commonest type, you call them as Vesuvian. And intensified Vesuvian, we call them as what? Right. And my dear friends, when I talk about the intensity based classification, what determines this intensity, if you ask me, it is the amount of gas that is emitted. More is the gas that is emitted, more will be the intensity. More is the gas that is trapped, more will be the release of gas. That's the reason normally we say convergent boundary, the gas being trapped, the possibility is more, the intensity is also more. Okay, that's all about this extrusive volcanic activity. And finally, what we have is intrusive volcanic activity. The magma, when it tries to come to the surface of the earth, if it is not able to reach the surface of the earth, and somewhere if it is getting solidified well within the surface of the earth, it forms this intrusive volcanic feature. And this intrusive volcanic feature, when it somewhere reaches the surface of the earth, how simple? If the land above it goes for an erosion, it can get somewhere exposed on the surface of the earth, possibility number one. Or there is also a possibility that somewhere the further push of magma can also somewhere make this, say for example, feature to rise towards the surface of the earth. Okay, whatever it is the case. If these intrusive features get exposed on the surface of the earth, then you call them as what? Intrusive landforms. You call them as what? Intrusive landforms. Okay. And these intrusive landforms are classified based on the shape and orientation. Very large in size. Very large in size. You call them as batholith. Vertical extension of batholith, we call them as stalk. Saucer-shaped structure, we call them as lopolith. Dome-shaped structure, we call them as lacolith. Combination of both, we call them as what? Phacolith. Horizontal feature, you call them as sill. Vertical feature, you call them as what? Dike. I repeat again. Very large, massive batholith. Minor extension of batholith, stalk. Saucer-shaped structure, lobolith. Dome-shaped structure, lacolith. Wavy pattern, phacolith. Okay. Horizontal feature, sill. Vertical feature, dike. Okay, right. Right, my dear friends. And I have also given you some of the list where you find the exposed such features. And among them, the largest intrusive volcanic feature is Dartmoor Range of England. And that's an example of exposed batholith. Okay. All other examples also I have just given it. With that, volcanic activity, we are completing it. Moving to the fifth topic of the day, earthquake. See, what is an earthquake? The sudden release of energy from a deformed rock, you call them as what? Earthquake. Wherever energy gets accumulated, there all I can have an earthquake. Where energy gets accumulated, wherever there is an inducement of stress, there all energy can accumulate. For example, when I say sudden release of energy, earthquake is all about sudden release of energy. It's all about sudden release of energy. Energy can get released suddenly only when there is an accumulation of energy. And when exactly energy will get accumulated, if you ask me, only when there is an inducement of stress. And this inducement of stress is largely due to plate movement or plate tectonic, but sometimes maybe by human activities also, right? So human activities can also trigger an earthquake. Such earthquake, we call them as what? Man-made earthquakes. But whatever be the case, right? The sudden release of energy, we call them as earthquake. And the place where exactly this energy gets released, we call them as what? Focus or hypocenter. And the place which is located exactly above the focus and on the surface of the earth, we call them as what? Epicenter. And the distance between this epicenter and focus, we call them as what? Depth of focus. We call them as what? Depth of focus. Okay. Or we call them as what? Depth of earthquake. And let me tell you, my difference, this depth of earthquake is inversely proportionate to the intensity of the quake. Intensity means deeper earthquake will be having less intensity, shallow earthquakes will be having more intensity. If you remember, I told you, right? Fold mountains of the world are known for shallow earthquakes. That's why the intensity will be less. And in that way, if you ask me where exactly the deepest earthquake is recorded, how deep we have recorded an earthquake, if you ask me, the deepest focus to be very precise, at 700 kilometers of depth. See, 700 kilometers of depth is not even lithosphere. It is mesosphere, right? Somewhere in the mantle. Somewhere very near to what? Say, for example, I should put it this way, right? Almost, right? 700 kilometers is mesosphere for that case, right? See, such a deeper earthquake may not affect or may not have a greater impact as such. But whatever be the case, the regions of deep earthquakes generally they are referred as Benioff zones. And Benioff zones are associated with subduction zones. Wherever subduction is taking place, that's where you call them as what? Benioff zones as such. Okay, right. Right, my dear friends. Now, having understood what exactly is an earthquake, my dear friends, technicality is very important. So, what is focus or hypocenter is very important. What is epicenter is important. Okay. Then, coming to India for a case, right? Let me tell you why exactly I'm just taking the case of India. Because when I talk about India, entire India is divided into different zones. According to NDMA's classification, there are 4 zones. Zone 2, Zone 3, Zone 4, and Zone 5. It's given here, right? 4 classification. In your atlas, it is given as 5, but NDMA's classification only 4, right? There is no zone 1 classification. Okay. So given here, my dear friends, particularly when I talk about zone 5 here, when I talk about zone 5, 7 regions are identified with zone 5. What is zone 5? Very high damage risk zone. Very high risk zone. It means probability of having an earthquake is very high. If you have an earthquake, the size of an earthquake will be large. Intensity of the quake will be more, right? The impact of a quake or the magnitude of this quake will be more, right? In that way, 7 regions are identified. What are the 7 regions? Kutch Peninsula, Kashmir Valley, Himachal Pradesh, Eastern Uttarakhand, Northern Bihar, Northeastern states except Sikkim, Andaman and Nicobar Islands. See, Run of Kutch, except Run of Kutch or Kutch Peninsula, the rest of the regions, if I take it, I find one thing in commonality. What is that common element, if you ask me? Directly or indirectly, they are Himalayas. Either they are in the extension of Himalayas or the indirect extension of Himalayas in the name of Andaman and Nicobar Islands. Andaman and Nicobar Island is also what? The immediate extension of Arakanayama Mountains and indirect extension of Himalayas. But whatever be the case, Andaman is also an example of fold mountain. It's an example of fold mountain. Okay. So there, my dear friend, somewhere we have an idea that there is a chance, yes, right, we may have, right, these regions are highly prone to earthquake for the simple reason. Again, what is a common element? Fold mountains. Wherever I have fold mountains, they are highly susceptible to what? Earthquakes. Even see randomly, when I search earthquake, right? When I talk about earthquake, Google itself suggests today, right? Even an earthquake in India, if you ask me today, they'll suggest. And most of the time you take it, it will be associated with some fold mountains, right? It will be somewhere near a fold mountain or a plate boundary as such. Okay. So again, putting a point that earthquakes are very common along the fold mountain regions. And I also told you that earthquakes can also be resulted by what? Human activities. Among them, normally the larger number of earthquakes, my dear friends, larger number, which activity of human being has created larger number of earthquakes, if you ask me, it is mining as an activity. Whereas if you ask me which earthquake is very devastating, human activity resulting devastating earthquake, right? Large earthquakes is construction of dams, artificial lakes, reservoirs, etc. And see, I can go for n number of examples, even over extraction of fossil fuels, shale gas extraction, heavy construction, even over extraction of groundwater also I can take it as an example. All right, see, logic is very simple. Wherever there is a large scale tampering of lithosphere, wherever there is a large scale modification of the lithosphere, there is a right large chance that it will be resulting in what? Earthquake. Either addition of weight or removal of weight, both. But the word large scale is very important. Large scale tampering of this lithosphere is important. Okay, right, my dear friends. Even see, even nuclear weapon testing, most of the places, even when India tested, right out, we have done this Pokhran test. The Pokhran test, the incident was actually recorded as an earthquake in the seismograms of the world. But only India said, no, no, we have tested our, say for example, the nuclear capacity. And very important, my dear friends, I have included etc. because net sources have given more than 700 different ways that how exactly earthquake can be created. See, I'm also sharing one bizarre incident. Why I want to share this bizarre incident, I'll tell you. Because somewhere I should ask myself the question whether this activity can result in an earthquake or not. This happened in 2018, my dear friends. Celebration, just a celebration. Football World Cup last year, Doha, Qatar, but 2018, Russia. The very first opening match between the defending champion Germany and the Mexicans. Mexico, compared to the stature of Germany, they were underdogs. Nobody thought that they'll be winning. Right? But surprisingly, Mexico won against Germany. When Mexico won against Germany, Mexicans who were seeing this match, out of excitement, out of joy, they started celebrating by jumping into the air. And the Mexicans landed together, right? That landing has caused one earthquake. That's what the news also says. I've just copied and pasted this news as it is, image, right? Mexican jumping for the joy at their country's surprise world victory or World Cup victory over defending champion Germany shook the ground so hard, they set off the earthquake detectors, right? See my difference, right? That's the reason we said even excitement can result in what? Earthquakes. That's the reason somewhere keep your answers always, options always open-ended. Right? Let's not confine that, okay, 1, 2, 3, this is the only way how exactly this earthquake can be resulted. Man-made earthquakes. Okay? Right. Now, apart from that, coming to the aspects. Every time I use this word called as intensity and magnitude. Right? Of course, we have the scale which refers, say, or measures the same. Richter scale and Mercalli scale. And my dear friends, the name itself says Mercalli intensity scale. It means Mercalli scale measures the intensity, whereas Richter scale measures the magnitude. Magnitude. Of course, India like country uses what? Richter scale. Right? Mercalli measures what? Intensity. Richter measures magnitude. So what is magnitude? Measuring the size of an earthquake, quantifying an earthquake. Richter scale, my difference. You just quantify an earthquake. You measure the size of an earthquake. You measure the amount of energy released and the shaking amplitude. You just quantifying an earthquake. You call them as Richter scale. Whereas, if I assess the damage that is caused by an earthquake, that's what I call them as what? Impact of an earthquake. If I somewhere assess the damage caused by an earthquake, right? That scale, we use it what? Mercalli scale. What is the damage? The damage can be what? Loss of life or loss of property. Somewhere you can say loss of men and material. So loss of this men and material, you call them as what? Intensity. See, there is a correlation. Higher magnitude earthquake may be high in intensity. That is okay, but not always. Okay. Now let me tell you, my difference. This Richter scale is a log scale with a base 10. What is this log scale base 10? By example, we'll try to understand. And if you ask me scale range, what is the scale range? Actually speaking, it is 2.0 to 10.0. But the image what I have used it would have said 1.0 to 10.0. One small correction. Only this 2.0, we call them as a feelable earthquake. So scale rating, actually, practically speaking, it starts with 2.0 and goes till infinity. Because the scale is open-ended scale. Right? The scale is open-ended. But we are using 10.0 because so far we have not recorded any double-digit earthquakes. And we are not interested also. Right? Whereas when I talk about Mercalli scale, my dear friends, Mercalli scale is a 12-point scale. So what is a 12-point scale? We have a pre-calibrated scale rating ranging from Roman letter 1 to Roman letter 12. As the number increases, the intensity increases. Right? Number 1 means instrumental, not felt by many, unless and until there is a favorable condition. Weak. Number 2. Say, for example, only if you are there in the upper floor of the building, slightly you will be feeling it. Then slight, moderate, rather strong, very strong, destructive, violent, intense, extreme, and cataclysmic. Cataclysmic means catastrophic. One word, total destruction. Everything is destroyed. Line of sight and level distorted. Objects thrown into the air. The ground moves in waves or ripples and large amount of rock moves position. Landscape altered or leveled by several meters. And my dear friends, they say in some cases even the route of the rivers can be changed. Such is that scale rating number 12. So it is 1 to 12. It is a pre-calibrated scale rating. Only thing is that you have to assess the impact of an earthquake and accordingly you'll be assigning a number to that earthquake. Okay, right. And when I talk about Richter scale, my difference. Richter scale, I said it is a magnitude scale. Sorry, it is a magnitude scale. Of course, it is a log scale with a base 10. Right, with a base 10. And what is the meaning of this log scale with base 10? I'll tell you. Simple. I'll go by the example. For example, if I'm just comparing 3 earthquakes, 2.0, 3.0, and 4.0. Assume that these are Richter scale rating. 2.0 in magnitude, 3.0 in magnitude, and 4.0 in magnitude. On the face of it, it appears that 4.0 is twice as large as 2.0. But my dear friends, let me tell you, every number that increases, shaking amplitude increases by 10 times and energy released increases by 31.6 times. It means 3.0 is at least 10 times more bigger earthquake than 2.0. 4.0 is at least 10 times more bigger than 3.0. It means 4.0 is at least 100 times bigger than 2.0. Why I'm using this word at least? Because if I take energy released, 4.0 is 1000 times releases more energy than 2.0. That's the reason I'm using this word at least. So Log scale base 10 means every number that increases, the scale or the size increases at least by 10 times, my dear friends. Okay, that is this base. Right. Now, all this, say for example, aspects of this measurement we have taken it. Now see, even somewhere the classes, when the beginning of this today's class, we talked about somewhere the news saying that the rotation of the core has stopped. Now comes the question, how exactly we have identified that the Earth's interior would have been looking in such a fashion, if you ask me? What has given the larger picture about the Earth's interior, if you ask me? It is all about studying the seismic waves. We call them as what? Seismology. Earthquake waves or earthquake is the one which actually acted as that windows to Earth's interior. Right? Windows to Earth's interior. In that way, during an earthquake, different types of waves are produced, my dear friends. You call them as what? Seismic waves. It means from the very focus, right, a pair of waves are produced, and they, say for example, travel only via the body of this Earth's interior. We call them as what? Body waves. And then when the body wave strikes the surface, that is epicenter first. From the epicenter, you have another set of waves, pair of waves that is traveling via the surface of the Earth. We call them as what? Surface waves. We call them as what? Surface waves. Okay. Now, during any earthquake, my dear friends, two pair of waves are produced. One, we call them as a body wave, and you call them as what? Surface waves. Okay. Body waves, as the name itself suggests, that it travels only via the body, internal or interiors of the Earth as such. They are produced from the focus, and a pair of waves is produced. What are the pair of waves? One you call them as P wave, and two you call them as what? S wave. Okay. And when I talk about surface waves produced from the epicenter, they are Rayleigh and Loud waves. Here, body waves are the one. Analysis of the body waves is the one which has somewhere given the idea about Earth's internal structure. Body wave analysis actually acted as that windows to Earth's interior. Whereas when I talk about surface waves, my dear friends, surface waves are the one which actually acted as that geomorphic agent. Earthquake has the potential to somewhere change the existing landform features. What wave somewhere generally changes the shape of the landforms or existing landform, if you ask me, it is all about surface waves. Okay. Surface waves, they're actually a geomorphic agent. But what has given us a larger idea about Earth's interior is this body wave. So first, we'll talk about this body wave, my dear friends. Okay. In that way, there are two body waves that is produced. One you call them as primary wave. Why you call them as a primary wave? Either you call them as primary wave or you call them as what? P wave. You call them as secondary wave or you call them as what? S wave. My dear friends, because P wave travels somewhere around 6 to 7 kilometer per second, not per hour, per second. 7 kilometer per second means nearly 25,200 kilometers per hour. Okay. So somewhere I can imagine the velocity at which this P wave is traveling. So any place, what will be striking first or what will be reaching first is what? P wave. That's the reason you call them as what? Primary wave. What follows primary wave is the wave next is what? Secondary wave. It travels half the velocity of this P wave, right? That's why you call them as what? Secondary wave. Now here, the wave property of this P wave, my dear friends, generally we call them as what? A compressional wave. When I say a compressional wave, what is the meaning? It travels in an alternate sequence of compression, expansion, compression, and expansion. Whereas secondary wave, if you ask me, my difference, they travel in, right, like a normal sine wave, they'll be traveling. Right, normal sine wave, they'll be traveling. Like a, right, they induce that shearing stress on it. So normally what happens, given the wave propagation, P wave is more like a sound wave. S wave is more like a light wave, my dear friends. Okay, in that way, when I talk about P wave, given the ability of the P wave to change the shape and volume of the medium through which it propagates, this calculation and all is not needed. Summary is very important. P wave can travel via both solid and liquid medium, right? Whereas S wave, because S wave has the capacity to change only the shape of the medium through which it propagates, right? S wave cannot travel via liquid medium. S wave can propagate via only what? Solid medium. Very important, my dear friends. S wave dissipates in liquid medium. They cannot propagate via liquid medium. Summary is very important. P wave can propagate via both solid and liquid medium. See, when I talk about Earth's interior, only two states of matters are there. Either it will be a solid layer or it will be a liquid layer. For binary purpose, asthenosphere is a partially molten layer. Asthenosphere is a semi-solid layer. But for binary purpose, better we'll regard asthenosphere as solid, never as liquid. Because it is plastic. It is not a liquid. It is plastic. Right? More you can treat it more like a solid, but not like liquid. Okay. In that way, only binary calculation, binary classification, I'm taking it either solid or liquid. Okay, right. In that way, my dear friends, I repeat again, P wave can travel via all the solid as well as liquid layer. But S wave can travel only through solid layer and it dissipates in liquid medium. Because of the fact, right, whenever an earthquake is produced, S wave tries traveling everywhere, but because I have the outer liquid core, S wave do not penetrates the outer liquid core, so nearly the other half of the earth do not experience this S wave. The other half of the earth which do not experience this S wave, my dear friends, collective regions, we call them as what? Shadow zone. We call them as shadow zone. The combined geographical location which do not record an earthquake, right, or which do not record an S wave during an earthquake, we call them as what? S wave shadow zone. S wave shadow zone strongly suggests the presence of a liquid layer in Earth's interior, and that liquid layer is nothing but what? Outer liquid core. Normally, from the focus till 103 degree on either side, I'll be experiencing what? This S wave. It will be recorded everywhere, but beyond it, I may not have it. This value will slightly change books to books. Some of the books you'll be finding 102, some of the books you'll be finding 105. Okay, but not beyond that. Okay. Whereas P wave shadows. Now comes the biggest question: how come P wave shadows? P wave can travel via both solid and liquid, but I understand whenever this wave travels or propagates from one medium to another, if it enters from solid to liquid or liquid to solid, there will be a kind of a refraction, a slight deflection in the path. The multiple refraction has also caused what? P wave shadow zone. So, S wave shadow zone strongly suggest the presence of liquid layer in Earth's interior, that is outer liquid core. And P wave shadow zone strongly suggest the presence of different layers in Earth's interior with different density and different state of matter. Between 103 to 142 degree, not only P wave is not recorded, S wave is also not recorded. So it is not only P wave shadow zone, it is also what? S wave shadow zone. Okay. But whereas 142 to 142, P wave is recorded, what is not recorded is what? S wave shadow zone. Or S wave is not recorded. Okay. So how exactly we have identified the Earth's interior is all with the help of the shadow zone analysis. Way back in 1930s, the depth of this core was discovered by Gutenberg. That's the reason this depth of core at, say for example, 2900 kilometer was named as Gutenberg's discontinuity. Okay, right, my dear friends. And surface waves, Rayleigh and Low waves, they move slightly lesser in velocity than S wave. They move in the respective motions. Rayleigh wave moves like a sea swell motion, whereas Low wave move in a whipping motion, and they'll be resulting in their own ground shifts, vertical and horizontal ground shift, respectively. So surface waves are the one. See, these waves, surface waves, are very disastrous. P wave is not disastrous, but surface waves are not very disastrous. But they are the one which act as the geomorphic agent. Okay, right. And this is all about earthquake. I have also given you all the waves and how exactly they propagate. Right. With that, coming to the penultimate topic called a tsunami, my dear friends. See, what is a tsunami? Tsunami means harbor waves. Literal meaning is harbor waves in Japanese. Japanese, you call them as what? Harbor waves. But if you ask me where exactly the genesis of tsunami, where exactly I'll be having the formation of tsunami, if you ask me, along the destructive boundary. Destructive boundaries are the one where I'll be having a subduction zone or a trench. You remember? Pacific Ocean, circum-Pacific zone is known for what? Trenches. And once it is known for trenches, it is also known for what? Genesis of tsunami. Why Japan is known for tsunamis, if you ask me, Japan is surrounded by trenches. Japan Trench, Aleutian Trench, Kuril Trench, Bonin Trench, Izu Trench, Ryukyu Trench, Philippines Trench, right? Marianas Trench, so many trenches we have, right? And of course, we call them as what? Seismic sea waves. It means these are sea waves, I understand. But these sea waves are created due to an earthquake. That's the reason always we say only a strong and shallow submarine earthquake may result in tsunami. Three conditions I'm using it, right? What are they? Only strong, more magnitude, and shallow, depth is very less, right? And submarine earthquake means epicenter is there in the ocean floor. Three conditions. Only a strong and shallow submarine earthquake may result in tsunami, even if three conditions are coexisting, right? Not every time it will be resulting in tsunami, right? If such an earthquake is happening, very strong earthquake is happening in the ocean floor, it may trigger a tsunami. Okay, right. Now here, tsunami is called as a harbor wave. In the sense, tsunami waves will be affecting only the coastal areas. Tsunami wave will not even affect the sailors of the open ocean because the wave nature is like that. For example, when talk about open ocean, tsunami waves or wavelength is great. The wave height is not so great. But as and when this wave strikes the coast, it becomes very, very gigantic, very gigantic. Okay. Now, why exactly the nature of this wave changes? Let me tell you, and let me tell you my difference, right? For example, I have just given you an example how exactly tsunami is triggered. That too, like a trench, right? See here. And talk about the subduction zone. Somewhere I understand trench. One crust is entering another. If that is the case, adjoining crust will also have a slight deformation. And if suddenly one crust slips over another, right? If one crust is slipping over another, right? I understand the sudden upliftment of the ocean floor can result in the formation of a mountain-like structure, right? Once a mountain-like structure is getting created, and this water can get transformed in all possible direction, you call them as what? Tsunami. For the formation of tsunami, a mount of water is needed in the middle of the ocean. And how exactly this mount of water is created? N number of ways. Number one, the default one, right? Sudden upliftment of the ocean floor, earthquake. Sometimes even submarine landslide can result in the movement, the mount of water. Or all of a sudden, when the submarine volcano get exploded, again the amount of water can be created. Or even a meteoroid strike with a high velocity happens, that can also create what? Amount of water. So, when exactly tsunami will be created, if you ask me, tsunami will be created when a mount of water is somewhere created in the middle of the ocean. Once the mount of the water is created, this water will start moving in all directions with great velocity, right? And of course, eventually it will be resulting in what? Tsunami as such. Okay. So what is the prerequisite if you ask me? Prerequisite is amount of water. Okay. Right, my friends. Now, when I talk about tsunami, one thing I understand, tsunami, open ocean versus the coastal areas, there is a significant difference. In that way, normally any wave, my difference, any wave, if I just talk about the wave character, see, the highest point of a wave, you call them as a crest. The lowest point of the wave, you call them as what? Trough. The height difference between crest and trough, we call them as wave height. The length difference between or the distance between two crest or two trough, you call them as what? Wavelength. In that way, when I talk about open ocean, deeper ocean, wavelength is very, very great. Longer wavelength, right? But wave height is not so great. But as and when it strikes towards the coast, it starts moving towards the coast. I understand this wave completely gets altered. Wave length will become less, wave height will get more, right? When it strikes the coast, my dear friends, it may rise up to somewhere around, say, for example, 30 to 50 meters. Sometimes beyond it also. 30 itself is what? 100 feet. 50 meters is somewhere around 167 feet. Okay. Maybe 100 to 200 feet. Why to take all the small, small numbers? 100 to 200 feet. It means the height of the water can rise to somewhere around 10 to 20 story building. Imagine, right? It becomes so gigantic in nature. And what exactly is the reason for the changing dynamic of this wave, if you ask me? It is all because of the shallowness of the coast. Okay. See here, open ocean wave height is not so great, only 6 meters. But 6 meters still I can call it as what? Somewhere mount. Because 20 feet. 20 feet is a great height. When it comes to mount water level that is being maintained. But the same 20 feet of water, when it strikes the coast, it rises to somewhere around 30 to 50 meters. Wavelength in open ocean is somewhere around 200 kilometers. Right? Image will be carrying 213, 213, but I am writing it as approximately 200 kilometers. But when it strikes the coast, it gets reduced to few kilometers. Velocity may difference. Open ocean, 700 to 800 kilometers velocity it travels. But when it strikes the coastline, it gets reduced to what? 30 to 50 kilometers. But still, 30 to 50 is a huge velocity. Now, why exactly the wave height increases, wavelength decreases, wave velocity decreases, if you ask me? All three, answer and reason is same. Because of shallowness. Shallowness. Shallowness is more like, say, for example, the deeper ocean, the height of the waves will not be so great. As it enters the shallow coast, it will start rising. Okay. Similarly, wavelength also gets, say, for example, somewhere truncated. And the velocity also, somewhere I understand, the shallowness will be applying a cause of a friction. Friction induced will be more. The velocity will start decreasing. Okay. But whatever be the case, right? Tsunami wave dynamics changes as and when it enters the coastline. Now comes the question, why exactly tsunami waves are destructive in nature? See, any sea wave, my difference, normal sea wave, if I take it, normal sea wave, normally I will be having a, say for example, the water movement. For example, I'll be having a continuous movement of this water. At one point of time, the continuity of this water will break. That is what we call them as what? Wave break. After the wave break, what happens is water will be splashing into the land. And the splash of this water is what we call them as what? Swash or surfing. You call them as what? Surfing. And all this surfed water will be once again going back to the ocean. You call them as what? Backwash. You call them as what? Backwash. You have surfing, you call them as what? Backwash. Now see, surfing is all about what? You go to a beach, see the sea wave, somewhere moving towards you. At one point of time, the continuity of the wave will break. Post break, what happens is water will be surging into the land, right? It will be surfing into the land. You call them as surfing. And once the surfing comes to an end, all this surfed water will once again go back to what? Ocean or the sea. You call them as what? Backwash. So pumping of this water into the land, you call them as surfing. The retreat of surfed water back into the ocean, you call them as what? Backwash. Now here, few things I have to understand. Number one, backwash will start only when surfing ends. Till surfing comes to an end, backwash will not start. Number one. Number two, the duration of surfing or backwash will depend on the wavelength. Normal sea wave, my dear friends. Normal sea wave. Normal sea wave. If you ask me what exactly will be the wavelength, normal sea wave. Wavelength is few meters. This few meters of wavelength, right, is resulting in surfing and backwash happening for few seconds. Forget about tsunami. Forget about sea wave. Come to tsunami. Tsunami, the wavelength when it strikes the coast is few kilometers, right? The wavelength is few kilometers. Surfing or backwash will be happening for few minutes to few hours. Normally, surfing or backwash happens for 20 to 30 minutes. It means nearly half an hour, right? Nearly for half an hour, 30 minutes. Even if I say seawater continuously enters at the rate of 30 kilometer per hour, I can imagine surfing will be happening for half an hour. Seawater will be continuously entering the land and it will be covering a distance of 15 kilometers, right? From the coastal line. Regions which is as far as 15 kilometers will get submerged. Surfing. And what is more devastating, I'll tell you, once the surfing ends, all that surfed water will be once again going back to the ocean, backwash. Right? So what makes tsunami disastrous is elongated surfing and delayed backwash. More the backwash is delayed, more disastrous it becomes. Okay. Now I can understand why exactly tsunami is more disastrous because it can submerge a larger areas as such, but not permanently. But that, say, for example, to and fro of the water can, say, for example, of course, cause a huge disaster and it can also change the existing landform. The beach deposits, the bar deposits, the estuarine mouth, the delta deposit, the sand spits, the stack and stumps, the geovalleys, coastal arc, coastal caves, n number of things it can change. Okay, right. So that's the gist of tsunami, my dear friends. I'm going to the last topic of the day, types of rock. See, types of the rocks, the questions are not asked much, but still, as a formality, let me take it and complete it. For example, three types of rocks are there. One, you call them as igneous rocks. Two, you call them as sedimentary rocks. And three, you call them as what? Metamorphic rock. What is igneous rock? Any rock that is formed out of magma, solidification of magma, you call them as what? Igneous rocks. Then what are sedimentary rocks? The name itself says sediments. See, for example, erosion. When you talk about erosion, when the rocks are eroded and these rocks are somewhere getting deposited, with the time, temperature and pressure, if the sediments are getting somewhere compressed to form a rock, you call them as what? Sedimentary rocks. Rocks found out of sediments. Okay. And a metamorphic rock. Whenever the rock changes its property, not only that, igneous rock can also become metamorphic rock. Sedimentary rocks can also become what? Metamorphic rock. If they change their property, right? You call them as what? Metamorphic, metamorphized. Am I right? Right. Now having a very general look of this igneous rock. See, an igneous rock forms out of magma and lava. Magma and lava both are same. Till it reaches the surface, you call them as magma. Once it reaches the surface, you call them as what? Lava. Molten rock material. Okay. And my dear friends, very important, these igneous rocks are known as primary rocks. Primary rocks. Why primary rocks? Because the magma itself is becoming what? Rock. And see, the Latin word igneous means fire. So somewhere I understand fire means volcanic activity. Volcanic activity itself means rise of magma. Correct. That's why you call them as what? Igneous rocks. So the magma cools and solidifies, it forms what? Igneous rock. Right. Now see, these igneous rocks, my dear friends, they are classified based on texture. Classified based on texture. Texture depends on size and arrangement of the grains or other physical conditions of the material. It is not so important, but still, I feel it is, say for example, we can take it, at least we can have it as a point. See here, they say, if the molten material is cooled very slowly at a greater depth, that is in Earth's interior, the mineral grains will be very large. Okay. Whereas the sudden cooling at the surface, obviously, once it reaches the surface, the rate of cooling will be larger, sudden. Because say for example, the temperature is comparatively colder. When in Earth's interior, it is warmer. The temperatures, the rate at which it is solidifying will be what? Taking more time. Okay. So the sudden cooling at the surface will be resulting in what? Smooth grains. So one thing I understand, extrusive rocks will be having smooth grains. Intrusive rocks will be having large grains. Okay. Intermediate condition, that and all you not needed, leave it. Okay. Now my dear friends, some of the, say for example, igneous rocks also I have just given it. Granite, gabbro, basalt, volcanic, tuff, or some of the examples of igneous rock. I'll give you. Right at the end, the last slide, I have just given you a list. That list is the popular names and easier names. Okay. Then comes sedimentary rocks. Sedimentary is derived from the Latin word means sedimentum. Means what? Settling, sediments. Explanation is not needed. So what they say, rocks, that is either igneous or sedimentary or metamorphic rock, whatever it is the case. If these rocks are somewhere exposed on the surface and if it is somewhere subjected to denudational process by some agent of gradation, that agent of gradation can be river, underground water, sea wave, right, moving glaciers or wind for that case, right. If it is subjected to this denudational agent, right, they are broken up into various sizes of fragments and pieces, and such fragmented transported by different exogenic agencies and deposited. And these deposits through compaction turns into rock. It's more like applying pressure. And this process of this, right, rock building materials, you call them as what? Lithification, right? Lithification. Litho means rock. Lithification is the process by which these rocks are being, somewhere it is getting collected and compacted. In many sedimentary rocks, my dear friends, a layer of deposits retains their characteristics even after lithification. Hence, we see a number of layers of varying thickness in sedimentary rocks like sandstone, shales, etc. Right? Some layers. Sedimentary rocks itself, you take it, you'll be finding plenty of layers, my dear friends, in that. Okay. Now here, depending upon the mode of formation, sedimentary rocks can be classified into three types. What are they? Mechanically formed. Right? Mechanically formed in the sense compaction. Right? Organically formed. Somewhere I understand, say for example, it is more like, say for example, sediments of organic material gets deposited, again compaction, again organic material gets deposited, again compaction. Right? And chemically also formed. And see one thing, all three, limestone is an example. Okay. So don't take limestone very seriously, right? Limestone can be mechanically formed, organically formed, chemically formed. But see, organically formed, one of the classical examples is coal. Coal is a sedimentary rock. Okay, right. Now coming to this metamorphic rock finally, my difference. The word metamorphic, when I say metamorphic rock, the word metamorphic means change of form. It means change of form. And very important, this is very, very important. These rocks form under the action of pressure, volume and temperature. Okay, volume and temperature. And time also you can take it for that case, right? Time also. Okay. Now in that way, my dear friends, metamorphism is a process by which already consolidated rocks undergo a recrystallization and reorganization. It means already a rock is there. Only say for example, right, reorganization and recrystallization if it takes place. You call them as what? Metamorphic rock. Okay, right. In that way, my dear friends, right? You also have, say for example, the property of this metamorphic rock that is being stored, right? In the process of metamorphism in some rocks, grains or minerals get arranged in layers or lines. Such an arrangement of minerals or grains in metamorphic rock is called as foliation or lineation, right? You will be finding like, say for example, lines will be there. Am I right? Sometimes minerals or materials of different groups are arranged into alternating thin and thick layers, appearing in light and dark shades. Such a structure in metamorphic rock is called as what? Banding. So, if I take the keywords, foliation, lineation both are same. Banding, right? All these, say for example, whether I have, say for example, layers of alternate thin and thick layers or the lines that is stored in the rock, foliation and banding, they are associated with what? Metamorphic rock. Then we have taken one keyword called as lithification. Lithification is associated with what? Sedimentary rocks. Okay, only the keywords are very important. Okay, metamorphic rocks are classified into two groups, my friends. One is foliated and two is non-foliated rocks. Both I have included in the example. Okay, so all the examples, if I just consolidate it, okay, igneous, I given more like intrusive and extrusive. Intrusive, the size of the grains will be more. Extrusive, the size of the grains will be very less. Basaltic, right? Dacite or classical example, right? When talk about intrusive, granite is more a classical example. Sedimentary rocks, sandstone, siltstone, right? Shale, classical example, right? Biologically, right? If it is getting created, coal, limestone, right? Dolostone, etc. They are also an example of what? Sedimentary rocks. Metamorphic rock, my dear friends, right? Skids, right? Or schist. Schist, when I talk about schist, schist is a classical example. Slate is a classical example, right? Gneiss or gneiss is a classical example. Am I right? They are foliated in nature. Non-foliated, right? Quartzites and marbles are classical example of what? Right, this non-foliated. So what I remember, what I somewhere I suggest, metamorphic rock, all the names are very important. Remember that these rocks are metamorphic rock. Sedimentary rocks, wherever you come across this word called a stone, my dear friends, mostly the word stones are associated with what? Sedimentary rocks. Am I right? Right? Stones. Coal is a sedimentary rock. Okay. Basalt, granite, or the classical example of what? Igneous rocks. Okay. Right. And I have also given you a rock cycle. This rock cycle, this grayscale image I have taken from NCRT. For example, magma resulting in the formation, solidification, igneous rocks. Igneous rock can also become metamorphic rock. Igneous rock can also be subjected to melting. Igneous rock can also get eroded and eventually become sedimentary rocks. Okay, right. On the other hand, when we talk about sedimentary rocks can be formed from the sediments collected from metamorphic rock or the sediments collected from igneous rocks. Am I right? Or the sedimentary rocks can be formed out of the sediments collected from the sedimentary rocks itself. All it is possible. Okay, right. Lithification process. And when I talk about sedimentary rocks, can also eventually becomes metamorphic rock. Right. When I talk about metamorphic rock, I understand already existing rock, either sedimentary rocks or igneous rock can become metamorphic rock. And all rocks is subjected to melting. Metamorphic is subjected to melting. Igneous is subjected to melting. Sedimentary is also subjected to melting. Okay, it's a rock cycle. The same thing, the adjoining picture gives you, right, animated colors. That's it. And my dear friends, these are the topics what we have taken for today, and somewhere we have just completed the same, right? So rest of it, right? Climatology. So tomorrow's class we'll be starting climatology with, right? Till then, right? We'll take a leave, and again the topic for tomorrow is also being, say for example, displayed already. It is given, right? So tomorrow we'll be starting and discussing about some of the very important topics in the chapter of climate.